Good evening, all. On behalf of Oasis Institute of Technology, Tiruchirappalli, Tamil Nadu, we take great pleasure in welcoming you to the AICTE Training and Learning Academy sponsored one-week faculty development program on quantum computing and AI, a potentially transformative synergy for future India, scheduled from 18th to the 23rd of August 2025 at 6 p.m. We are privileged to have with us eminent speakers, respected dignitaries, faculty members, and enthusiastic participants who have joined to begin this week-long journey into the exciting world of quantum computing and artificial intelligence. Let us now commence the inaugural session.
We invite Dr. J. Palanivel, coordinator of this FDP, Oasis Institute of Technology, to deliver the welcome.
Good evening, all. Respected Chairman of Oasis Institute of Technology, Managing Director of Oasis Group of Companies, respected Principal Dr. Antos Britus Kingsley, and the co-coordinator, Mr. Joshua, respected resource persons from premier research centers, universities from India and abroad. A warm welcome to all of you. My dear participants, faculty members from Oasis Institute of Technology and the other institutions of India. Thank you very much for joining us in this meeting. I am profoundly grateful to ATAL Academy for giving us this opportunity to conduct this FDP on quantum computing and AI, a potentially transformative synergy for future India. We know that technology has always been transforming the world scenario, especially quantum computing is one such thing. If you look back the history in the past, this has never had happened because always technology is taking twists and turns and gives us surprise and making radical change significantly in our basic lifestyle. In that sense, quantum computing is having a great potential, and the convergence of quantum computing and AI holds immense potential to bring in a lot of changes which we cannot imagine. Especially, this quantum computing can accelerate AI, which leads to powerful algorithms and effective data analysis. A lot of things are waiting for quantum computing in the drug discovery, material science, and finance industry. So it is our duty to educate all our students, let them be prepared for what is going to happen in the coming years with quantum computing. So, as ATAL is expecting, we are training and we are giving the faculty members this great opportunity to get themselves familiarized with the quantum computing technology and how it is going to have its synergy with artificial intelligence. I believe all the participants will get benefited. In turn, they will be shaping all our students to have a better future India. Thank you very much for this given opportunity. Thank you.
Thank you, sir. We now invite Dr. A. Ambrose Kingsley, Principal, Oasis Institute of Technology, to felicitate the gathering.
Respected resource persons, respected coordinators and team, dear participants, good evening to you all. ATAL Academy is giving a lot of opportunities to all the faculty members to develop their skills by organizing several faculty development programs in both online and offline modes. In this occasion, I would like to thank the ATAL Academy for giving us the opportunity to organize this FDP in our institution. Our FDP title is related to quantum computers, and we know the quantum computers are going to change the world technologically in the coming years. So, keeping updated in the quantum computers is very much essential for all the faculty members. I hope this faculty development program will train all the participants and will keep you updating in quantum computers. I really appreciate the coordinator, Dr. J. Palanivel, and his team for their efforts in organizing this faculty development program. I wish this faculty development program is going to be a grand success. Wish you all the very best. Thank you.
It gives me immense pleasure to introduce our first distinguished speaker, Dr. Gururaj Kadiri, who is currently serving as a Scientific Officer G in the Material Sciences Group at the Indira Gandhi Center for Atomic Research, hereinafter IGCAR, Kalpakkam, India. Dr. Kadiri has rich research experience in areas of material sciences with a special focus on computational modeling and quantum systems. He has contributed significantly to research in advanced materials, particularly in areas relevant to nuclear and quantum applications. His work at IGCAR involves exploring the intersection of quantum mechanics, material research, and artificial intelligence. Doctor has published lots of research publications. We are more than privileged to have him here with us today to deliver his lecture on the history and evolution of quantum computers and its role in AI. His expertise will provide us with a strong foundation to begin our FDP. Thank you.
Dear participants, Dr. Gururaj will start his presentation right now. The participation, if they are having any queries, please post all your queries in the chat box and please mute all your microphones. Thank you very much.
Yeah, good evening. Let me just share my screen, then I can continue. Yeah, is my screen visible to all of you?
Yeah, yes, sir, it's visible. Thank you.
It is visible. Okay. Okay, fine. Yeah. So I'm Gururaj Kadiri, and let me start by thanking the organizers for giving me this opportunity. Uh, I particularly want to thank Chairman Sri Ilangovan sir, Principal Anto Spiritus Kingsley sir, Coordinator Palinivel, and Co-Coordinator Mr. Joshua. They have taken very commendable steps in organizing this, and ATAL Academy has helped immensely in this activity. I really believe this is a very good initiative combining quantum computing and artificial intelligence, because this is something like artificial intelligence is today. We are seeing it all around us, and quantum computing is going to be tomorrow, where we are going to see great impact of quantum computing in our day-to-day technological as well as in our daily life. So bringing together these two topics is definitely going to have a transformative potential for this country. So I commend the Oasis Institute for taking up this theme for the faculty development program. So let me start the first session. Again, I want to say that it is a challenging task for me to start the 1 week proceedings, to make an initiative to start this activity, because if somebody has started before me, then I can see how the trend is, and I could have changed my talking style or my slides. Since being the opening batsman, I have a lot of responsibility to steer this program in the proper direction. So I am thankful for this opportunity. So let me start the actual talk here. Am I audible to all of you?
Yes, sir, you are audible. Audible to
Okay.
us.
Yeah, great. So shall I begin the talk now?
Yeah.
Okay. So I have titled the talk as the history and evolution of quantum computers and its role in artificial intelligence. Again, I am going to spend most of the time on the quantum computer part, because that is where my specialization is. And I am going to touch upon how it is expected to impact in the artificial intelligence, particularly in the machine learning and in the context of big data. Okay. So I'm sure there are more capable people in the coming days. They are going to enthuse in artificial intelligence. Then you are going to realize how quantum computers are going to impact there. Okay, so the moment there are some talks on artificial intelligence, then my today's talk is going to become more informative and more useful on the AI part of it. Otherwise, on itself, quantum computers has great potential. So we are going to understand. I am going to be very slow here. I don't have many slides, so I am going to go very slow. And if you have any difficulty, I'm sure there is a mechanism. The institute will follow up it to me. Even as we speak, you can very well interrupt me and ask any clarifications. I just want to know what is the specialization of the audience. Are most of them physicists or engineers? How is it?
Yeah, most of them are faculty members from engineering colleges and universities.
Okay, great. So, so you can very well interrupt me at any point. I will more or less pitch it like a classroom lecture, but it need not go like that. You can interrupt me at any point, and you can ask your questions, and I would be more than happy to answer it. Let this talk be very informal and very learning experience for both of us. You can suggest your ideas, and we can have a very conversational talk. Let it not be a one-sided affair here. Okay. So let me start very formally. Okay. So this is going to be the scheme of my talk. Are the slide transitions all right? I hope you are able to see the second slide, because sometimes the screen gets stuck in the first slide only. So yeah, so this is the scheme of the talk. So I'm going to introduce, most of you will be familiar with the classical computers. So I'm going to discuss how a classical computer is built in the theoretically. Okay, so how a classical computer is built, and then what features do you add to a classical computer to make it a quantum computer. Okay, so then I'm going to discuss adding those features of quantum systems. What new capabilities will your classical computers acquire? Okay, what are the new quantum features, and adding them to a classical computer, it becomes a quantum computer. And what new features do they demonstrate, do they display? Okay, then how were the first ideas of quantum computer conceived? And then I'm going to introduce you to the very interesting notion of quantum supremacy. Okay, then so these four are the topics that are fundamentally about quantum computers, and the other two of them are about the machine learning problems, which I take it to be part of the artificial intelligence part of this lecture. Okay, so this is where my expertise lies, and this is where I am going to pitch it for the rest of the speakers. I am going to make a claim here, and I'm sure the other speakers are going to take forward the ideas that I have presented here. They are going to do a much better job in explaining how quantum computers can help in these two aspects. But my syllabus is more or less, I'm going to talk about the quantum part, and of course I'm going to explain what I think will play a role, how quantum computers will play a role in the other two aspects as well. I'm going to discuss them, but you will get more appreciation as you hear more about the artificial intelligence side of this particular faculty development program. Okay, so let us begin with the first topic. What all can a classical computer do? Okay, so this part is a little tricky, because when we say classical computers, what do we mean? What all computers are counted here? Okay, because what can a classical computer do can mean different things. Your computer may do different things than what I have. Okay, ordinary computer, a laptop costing 20,000 may do different things than a supercomputer costing say 20 lakhs or 1 crore rupees. Okay, there are computers which cost you upward of say 50,000, 50 lakh rupees. Of course, they are going to do much more things than what a 20,000 computer can do. Okay, one can even argue that a phone is also a computer. Okay, that way a phone can do very different things than what a computer can do. Okay, so what a classical computer can do is a very difficult question if you don't frame the question properly. Okay, so we have to ask a question which are going to encompass all the features of the current day computer, and which are going to include all the features of the classical computers that are going to come tomorrow also. Like there could be a powerful GPU based computer, there could be why only 32 GB RAM, you could have a 64 GB or 1 terabyte RAM. Okay, then you can ask a question, what can that 1 terabyte computer can do that today's computer cannot do? Okay, so there is always this question among people, how quantum computer is going to be different? Is it going to be a faster computer? Okay, if it is faster than today's computer, then it may be as good as tomorrow's computer, tomorrow's Intel laptop, or Intel laptop that is going to come say 10 years down the line, the Snapdragon processor and all. So how is it really going to be different? Is it just a faster computer, or is it something fundamentally different? That is a question we always get in this field. Okay, what is special? Is it just faster, or is it something else? That is the question. Okay, so for that to know, we have to know what all a classical computer can do. Okay, so let us start with the classical definition of a computer. Those of you who are from computer science or electronics background will appreciate this particular treatment. There is a notion of Turing machine. How many of you are aware of this Turing machine? I'm sure the computer science people will be knowing of this Turing machine. A Turing machine is a simple abstract model of computation. Okay, it is an abstract model. Why do you need an abstract model of computation? Because you don't want your definition, whatever you are going to say, you don't want that to depend on the current computers. Okay, what you are saying should be true for all the computers that are going to come and all the computers that have come till now. Okay, so for that we need to have an abstract model of computation, something that does not change between say Intel processor or any other processor, or say 32 GB RAM or 64 GB RAM. The statements that you are going to make should not depend on the details. It should depend. So you do not want them to depend on the details. So that is why you are going to talk about an abstract model. It should not be something, whatever you are going to say should not change from one PC to another PC. You want to make a general statement about what is possible on a computer. Okay. So here there is a notion of what is known as a Turing machine. Okay. Turing it's a name. He is a name of a scientist, Alan Turing. He is an Englishman. He worked during the Second World War time, a brilliant mathematician and a theoretical computer scientist. And he also did a lot of work on quantum communication, not quantum communication, the classical cryptography, the classical communication also he has worked. So this person, Alan Turing, he gave a definition. He gave a first definition of a quantum computer. This goes by the name of Turing machine. Okay, a Turing machine is going to contain an infinite tape. Okay, this picture, all of you are able to see. Look at this picture on the left bottom. You can see this picture on the left bottom, right? So you have an infinite tape. Okay, you have a tape. Imagine it's just a one-dimensional tape. Okay, what is written on the tape? What tape is going to divide it into cells? Okay, each one is a cell. Okay, each block is each square is a cell. Okay, each cell is going to contain a symbol. Okay, it is going to contain a symbol. Okay, the symbol, for example, in this case, it is a binary symbol. Okay. Okay, I am excuse me, I am pointing with my there is a laser pointer. Is this visible to all of you?
Yes, sir. It is visible, sir.
It is visible. Thank you. Yeah. So you can see a red color blob that I am pointing. There is an infinite tape, and the tape is divided into cells. Each one is called as a cell. What is written in that cell? Some numbers are written in that cell. Okay, what could be a numbers? That numbers could be any alphabet. It could be A, B, C, D, or 0, 1, 2, 3, 4, 0, 1, 2, 3 decimal numbers, or it could be binary numbers, hexadecimal. That details do not matter, but there are some things written on the head of this, on the tape. Okay, on the cells of the tape, you have written some numbers on the tape. Okay. And there is another one known as the control unit. It is going to contain, it is called as the head. You can look at this yellow colored object here underneath the tape. There is an yellow colored object that is known as the head. Okay, what can head do? The head is going to read the contents of the tape. Okay, what are we describing? I am describing to you what is known as a Turing machine. I am describing a Turing machine. What is Turing machine? Theoretically, it is going to be a model of a computer. Model of a computer. Okay. Okay. It is going to describe any computer. Okay. Any computer can be described as a Turing machine. Okay. Why do you require this theoretical machine? Because we want to understand what a Turing machine can do. Okay, whatever a Turing machine can do, a computer can do. Whatever a Turing machine cannot do, a computer cannot do. Is this clear to all of you? A Turing machine is going to be a theoretical model. It's a theoretical model of a computer. Okay, whatever a Turing machine can do, your computer can also do. Whatever a Turing machine cannot do, no matter how powerful your computer is, it cannot do. Is this fine? Is this clear to all of you? Yeah. So this is a theoretical model of a computer. I am explaining what are the features of this theoretical model of a computer. So here you have a Turing machine, which is an infinite tape divided into cells. These are all the cells. Again, I am pointing to the left side bottom picture, and there is a head. Okay, the second statement is it should have a head that can read and write symbols on the tape. What this head will do, it is going to, suppose it is, now the head is pointing at the third cell, right? The first cell has entry 1, second cell has an entry 0, third cell also has an entry 0. This control unit, this head, is reading the symbol that is there in the third cell, which in this case is 0. Okay, and you can see what is there in the control unit. What is the, it is written state Y. All of you are able to read that it is a state Y. Okay, state Y. This head is going to also contain some states. Okay, the head is going to exist in certain number of states. Okay, it could be like state X, state Y, state Z, or state red, green, blue, or state sad, happy, angry, whatever states. Okay, so there are, it can exist in a certain number of states, and there are tape which can have alphabet symbols. These symbols could again be, it could be binary alphabet, or it could be decimals, or it could be numbers, or it could be English alphabet. It could be any symbols on the tape. The state could also be any symbols, any finite number of symbols, which in this case is state X, Y, Z, or state PQR, or state red, green, blue, whatever. Okay. Now, what this is going to do is, your control unit is going to begin, say, from the left end. Okay. The tape is infinite to the right, but it starts from the leftmost point, and it is potentially, it could be infinite. Okay. So your state, your Turing, this Turing machine is going to have a head that is going to start from the leftmost symbol. Okay. It is going to read what is there. What is there on the first symbol? What is there on the first cell? What number is there?
Number 1, sir.
Number 1. So there is a number 1 is there. So it is going to read that number, and it is also going to see what is the state that is in. Okay. It is in the state Y. Okay. So there are some rules. That is what the fourth statement tells you. There is a finite table of instructions. What? So that instructions are going to tell you, if you read the number 1 and if the state is Y, it will tell you make 1 to 0. You flip that index, say make 1 to 0, and move to the next symbol. Is the rule clear? The rule is, for example, the rule could be that if you are reading the symbol 1 and when your state is Y, you change the symbol and change your state. Suppose the symbol is 1, then make it 0, change the state from Y to say Z, and move one step forward. Okay. Then this 1 becomes 0, the state now becomes X, then it comes to 0. Then there is another rule. If it's, the rule is, if the symbol is 0 and the state is X, then move one step to the right or one step to the left, depending on what the rule is. Again, you change the symbol or you don't change the symbol, you change the state or you don't change the state, and then you move one step forward, okay, or backward, depending on what the rule says. Okay, so what is this is, you have a collection of rules. These rules are going to be like your program. These rules correspond to your program, whatever Python or C++, okay, that you are using, Python or Java, whatever programs you are using. This is going to model those programs. Okay, this is going to be like running those programs. Is it clear? And what are the contents of the tape? The contents of the tape are going to be your input file. Okay, the rule is going to be your processor. The head is like your processor. Okay, so the processor has some program. The program tells you, if the entry is 1 and your head is in the state X, you move one step forward. Then if you read a 1, then you move one step backward. Like that, you are going to move forward and backward depending on what your program is. Okay, so let me go back here. Yeah, all of you are able to see what is happening here. I will explain to you. Just look at
yes, sir. It's very interesting. Yes, sir.
Yes. So I will explain to you what is happening here. Let me rerun this program. All of you focus your attention on the right side animation, bottom right. bottom right animation. What do you have it? What are the contents of the tape? The contents of the tape are 010010. Okay, this is what is given as the input. This is the data. What is this Turing machine going to do? A Turing machine has to do something. The Turing machine, I said, is a computer. A computer has to do something. Okay, we are asking it to do a specific job. What is the specific job? It should identify whether a binary number is a palindrome or not. Okay, I hope all of you remember what is a palindrome. Okay, a palindrome is a string that is going to read the same, whether you read from left to right or right to left. Right, all of you remember that definition. When we were in our MSc or in BSc, we used to write programs, no, identify something is a palindrome. That used to be our first program, very early programs we used to write. Okay, so this is one such program. Now we are not doing it in Java or Python or C++. We are doing it in which language? We are doing it in a Turing machine. Okay, very interesting, because if you can do it on a Turing machine, you can do it on a computer. If you cannot do it on a Turing machine, you cannot do it on a computer. Okay, since we know we can do it on a computer, we have done it when we were young, so we know we should be able to do it on a Turing machine. Okay, it may not be possible for us. We don't think in the language of Turing machine. It may be difficult for us, but definitely it is possible. Okay, so I have given an example where I picked it up. Again, I did not discover this myself. I picked it up from some internet. So this is the input string given to you is 010010. Okay, this is a six binary digits are there. This is a string of 6 binary digits. I want to know whether it is a palindrome or not. Okay, by the look of it, is it a palindrome or not? Yes, it is a palindrome. Okay, yeah.
Yes, sir. It's palindrome.
Yes, it is a palindrome. So we want to see how, whether it is going to work or not. Again, recall whatever are the instructions that I have given to you about the Turing machine. I have now erased all that I have written, so you can easily see a Turing machine consists of an infinite tape. The tape is not shown to you, only the contents of the tape is shown. Okay, now the contents of the tape are the inputs to the program. The input is now 010010. Okay, and your head is now starting from the leftmost digit, so it is now reading a 0. Okay, and I told you the head is, what is it going to do? It is going to replace the contents with either 1 or 0 or blank. Blank is a special symbol saying that the string is empty, the tape is empty, because the tape I told you is infinite, but you have only 6 digits. Then what are six cells only are filled with a 0 or 1. The rest of them are empty. So how do you tell the program that rest are empty? By putting a blank symbol. Okay, so the program will have a rule on what to do when it sees a 0, what to do when it sees a 1, and what to do when it sees a blank symbol. There are 3 symbols possible in this example: 0, 1, or blank. Okay, now let us see what is happening. You can see, yeah. Okay, so this, it has, what it has done is, it has again, you observe carefully, it reads a 0, then goes one step to the right, reads a 1. Okay, okay, what this is going to do is, it is going to read a 0. Let me first, it has read a 0. Okay, then it has just gone to the rightmost point until it encounters a blank symbol. Okay, once it sees a blank symbol, it comes back to the left. Okay, and then again it checks whether the rightmost symbol is the same as the leftmost symbol. If it is same, it is going to delete both of them. Just see what is happening here. Yeah, now it has gone to blank, then it has come back, it has eliminated both the zeros. Okay, so all of you are following how it is doing. It is going to first read what is there on the leftmost, then it comes back to the rightmost digit. How does it know what is the rightmost digit? Because the rightmost digit is going to have the next symbol as empty. So whatever is the blank symbol, it comes to the left and reads that. That is going to be your last symbol. Okay. So once he reads, it compares whether the last symbol is same as the first red symbol. Once it is there, it is going to delete both of them. Okay. So again, I am going to run this. Yeah. So you have now it is 1 0. Now it is 1 0 0 1. Then after that 1 1 also gone. Now you have 0 0. Now 0 zeros are eliminated. Once you encounter a totally blank string, you know it is a palindrome. Okay. If it is not a palindrome, then something will be left over. Okay. Of course, we are assuming it's an even digit. Okay. If it is an even sized, this program is going to work. If there are even number of bits, it can identify how many, whether such a binary string is a palindrome or not. Okay. Is this example clear to all of you of what is a Turing machine?
Yes, sir.
Yeah, thank you. Yeah. So I request you to keep answering my questions so that I know whether I am able to communicate. Okay, let us go very slow. We have a lot of time here. So please be responsive. If you have any questions also, maybe you should ask. Of course, it is the OASIS will decide whether you should how frequently you can interrupt, but it is fine with me. Okay. Yeah. So after this illustration of Turing machine, we now enter into a very bold prediction, which is known as the Church-Turing hypothesis. What is the name of this? Church-Turing hypothesis. Again, these are the names of two people. This is a Church. He is another, I think he is an American physicist. Turing, we told you, is a, I told you he is a British physicist, British mathematician. He is an American, he is a logician, he is not a physicist, I'm sorry. Church is a mathematician, a logician, a logic person studying logic, and Turing is a British mathematician. Together, they have come up with a Church-Turing hypothesis. Okay, what this hypothesis tells you is that any calculation that can be done by any realistic physical device, okay, very powerful statement. It tells you any realistic physical device, any calculation that you can do can also be done by a Turing machine. Okay, this is a very powerful assertion. This is a very powerful assertion because it is telling you that if you can do some computation with a Turing machine, if you can, any computation that you do with your state-of-the-art computer, you can also do it with a Turing machine. Conversely, if you cannot do something with a Turing machine, you cannot do with any other machine. Okay, that is a converse statement. This is even more dramatic statement. If a Turing machine cannot do something, no computer, no matter how advanced it is, it can solve it. Okay. Again, I know some of you might be wondering what happens to quantum computer. Okay, because this whole week-long program is on quantum computers and how it is going to revolutionize our lives. And here I'm making a claim that no computer is better than Turing machine. Okay. Okay, no computer is better than Turing machine. Okay. Okay, so there is something you should realize that this is before quantum. This claim was before quantum computers. Okay, they have not anticipated quantum computers. So if quantum computers come, then Church-Turing hypothesis will be broken. It will be proven wrong. Church-Turing hypothesis, CTH, I will say, CTH will be proven wrong when quantum computers come. Okay, quantum computers are going to prove the Church-Turing hypothesis wrong. Okay, what is the Church-Turing hypothesis? The Church-Turing hypothesis tells you that a Turing machine, again, what is a Turing machine? Go back. A Turing machine is this particular machine which has an infinite tape. There is a head which definite states on it, and there is a program that is going to tell you if this case you move forward, if you read this input and this, then you move one step forward, then you change the state of the head state, or the tape contents are also changed. Any such rules are sufficient to do any complicated simulations. Any complicated computations can be done just by this kind of logic. Okay, so the Church-Turing hypothesis tells you that all this is, the Church-Turing hypothesis is going to tell you that all this is what is possible. So all sufficiently powerful, again look at this, all sufficiently powerful computer systems are essentially equivalent. Okay, very powerful statement. Whether you are working with a 10-year-old PC i3 or P2 machines, anybody remembers those machines? P1, P2, the Intel before I generation came, we used to have this P2 machine, then P3, P4. P3 was not there, I guess. P3 was very short-lived. It was P2 and there was P4. Okay, all these are today's computers with your GPU, accelerated RTX cards and all. They are essentially equivalent in terms of what problems they can solve. Is it clear? This is a very powerful statement. I want all of you to appreciate this point. Any sufficient powerful computers, all computers are essentially same in terms of the problems that they can solve. Okay, some computers can solve it faster, some computers will solve it slower, some computers will solve it more efficiently. All right, but they all can solve same class of problems. They cannot solve different class of problems. Okay, you understand that? Because you should also know that not all computers, not all problems are solvable by a computer. Okay, this is another powerful statement. Not all computers, not all problems can be solved on a computer. Okay, not all problems can be solved on a computer. Okay, then okay, this is an interesting statement. Okay, so can anybody guess what sort of problems cannot be solved on a computer? I am expecting answer here, a short one-word answer perhaps.
For a hypothetical questions.
Okay, what sort of questions? Yeah, good. Okay, I get your point. Hypothetical questions like which do not even make sense. Okay, like which are not even mathematically well posed. Okay, like is there any planet in which Sunday comes after Monday? Okay, that kind of questions, they don't even make sense. So maybe quantum computers, your computers cannot solve that kind of questions. That is fine. Any other problems which are in the domain of mathematics? Why I am insisting mathematics? Because mathematics, if you pose a question in mathematics, then it becomes a well-founded question. It is not a illogical question. Okay, so so can you think of any question in mathematics which even a computer cannot solve? Okay, when I say mathematics, don't assume that that I am running away from physics or chemistry or biology problems. No, when I say mathematics, it includes all our real world problems. Okay, real world problems are real world physical problems. Okay, not emotional or spiritual problems, but real world physical problems are all mathematical problems. So there is absolutely no harm there. Okay, in limiting to mathematics. Okay. Yeah. Any answers in particular respect to mathematically formed problems?
So what about Riemann hypothesis?
Riemann hypothesis. Yeah, very good question. Okay. Are there any? Yeah, you have this Riemann hypothesis. What is the Riemann hypothesis? Or any of those problems? Okay, you have Fermat's loss theorem. Any of those problems? Can we know what there are? There is another one such problem. I'm now forgetting the name of that. Okay. Yeah, fine. Yes, that is a good point. Any of those mathematically unsolved problems can we solve? Okay. There is a Poincare problem, how much packing you can do, whether what is the best way to pack an object in 3D. Okay. So many of those kind of questions can we solve it? Okay. Are there any unsolved problems? Okay. Can a sufficiently good computer solve that problem? Okay. Yeah, that is a good input there. Yeah. So what does Church-Turing hypothesis tell you? With respect to such questions, what does Church-Turing hypothesis tell you? It tells you that if there is any computer that can do, then your computer also will do. Okay, you should assume that having a very poor computer will take ages. If you have an advanced computer, maybe it will do it in 1 day. Your computer may do it in 6 months. Fine, but it will be solvable. Okay, I will explain in which sense quantum computers are better. I will explain to you when I come to quantum. But right now we are all doing classical. There is no quantum at this stage. Okay, so I want to limit ourselves to only classical. Okay, so we are only doing classical computers. Classical computers are all the computers that are based on this Turing machine notion. They are all equally powerful, and if one computer can do, another computer can also do it. Okay, it can do it rather slowly, or it can do it, yeah, in the same program. If one fellow does it in 1 day, the other fellow may take 6 months or 1 year, but they are going to solve the same problem. Okay, so if there is a way, like you said, the Riemann hypothesis or Fermat's theorem, whatever, if any mathematically Fermat's theorem or any problem in physics or chemistry or mathematics or biology, if one computer can solve it, then another computer also can solve it. Okay, so in other words, all computers can essentially solve the same set of problems. Okay, yeah, I will take a small digression here. Since we have come to this point, let me ask a question. I will introduce you to something known as the halting problem. I will write here halting, HALTING, halting problem. Okay, halting problem. All of you note down. I mean, during your free time, I request you to, yeah, I request you to look up this halting problem. Okay, this is an interesting problem which is unsolvable. Okay, halting problem is unsolvable. Okay, what is halting problem? Very interesting. I want all of you to focus. Halting problem tells you what it does is it is going to take a program. You know, we write our programs. No, you remember all when we were very young. If you write a bad program, what happens? What is the worst mistake you can do while programming? One is the programming, it doesn't work. That is fine. The program doesn't work. It gives an error. It gives a compilation error, or syntax error. Syntax error. Yes, it gives a syntax error. Or the program compiles correctly, but you don't get the answer. Right? You want what is 3 into 4? It tells you 136. Okay, that is fine. That is one type of error. What is the more dreaded error? Or which error is more scary?
Putting into a infinite recursion.
What, sir?
Putting the processor into a deadlock, like a infinite recursion.
Perfect. Yes, perfect. That is the most dreaded error, where your program neither gives you the right answer nor it tells you an error. It just keeps on running. Right? That happens.
Yes. Hanging,
okay?
hanging.
That is what we call hanging. Okay. It is a very dreaded thing because you don't know whether you just have to wait for another second. Maybe that hope we also have. No, maybe it is running. If I just wait for 1 more second, it is going to give me the answer. But another part of the mind is will tell you that no, it has stuck there, system hang ho gaya. So you have to do, what do you do then? You do Control Alt Delete, or if you are very impatient, you are going to press the restart button, right? All of you have faced this problem. We all have faced this problem, right? Yeah. So what is the problem? The problem is halting problem. As we had a response here, if the program neither, so the program will neither exit, I mean, it should exit. The program should halt. Okay, that is the meaning of halting. The program should halt. What is the meaning of halt? It should stop. Okay, it should halt. Okay, whether it gives the wrong answer or right answer, that we will see later on, but it should halt. Okay, but suppose this is the program never halts, then it is a very scary situation. So the halting problem, if there is, suppose, what is the halting problem? What is the halting problem? The halting problem is knowing, given a code, okay, given a code. Suppose there is a program that tells you, that reads your program, okay. You have written some program. The program is to find whether some text hello is coming in, say 1000 page document. You have 1000, you have suppose 1 million pages are there in it. You have a 1 million page document. In that you want to know whether Tamil Nadu is appearing. Okay, you want to search for 1 million pages are there. You want to search for a specific word called Tamil Nadu, whether it is appearing or not. Okay, one thing is, the program will tell you if it is appearing. The program should tell you it is appearing. If it is not appearing, the program should tell you that it is not appearing. But it should do that, and it should halt. It should tell you yes and stop. If it tells you which page number or how many times, that is even better. But we are not even asking that. We just want to know whether a particular word is appearing in a particular document, say huge document, say 1 million pages, whether a particular string is appearing or not. It should tell you if it is appearing, yes. It should tell you if it is not appearing, it should say tell no. But either way, it should halt. It should not, even if it tells you unable to find, that is also all right. If it tells you I cannot find, that is also fine. But it should be able to stop. Okay. So suppose there is a miracle machine. Okay. Suppose there is a miracle machine. There is a miracle machine or a miracle program. Okay, miracle program. Okay, what this miracle program will do? It will take your program that you have written, okay, and it is going to check whether this program will halt or not. Is it clear? Okay. Is this clear? What is this miracle program going to do? It is going to check whether you have written your program correctly or wrongly. Okay. It will check whether this. Yeah. Any questions?
Yes, sir. If we understand.
Yeah. Okay. So if there is any program that is going to tell you a miracle program, the name I have called it miracle program. Okay, don't take it seriously. The name is not important. Suppose there is a program that is going to tell you if your program is going to halt or not. Okay, it would be good. It would be very good. Correct? Yes, it is very good. Okay, so you want to know whether such a program can exist or not. That is why I call it a miracle program. Okay, a miracle program, what it is going to tell you? It is going to tell you whether a given program, okay, you have a miracle program. To that, what you send as input, you send your own program. You have written a program that is going to say multiply two numbers or whatever. Okay, you just want to know whether this program is going to halt on all inputs or not. Okay, is it going to make your system hang, or is it going to execute it properly? That is your interest. Okay, That is a very useful program, right? It will be a very useful program. Okay. Why it
Is
is
it a
useful?
kind of script, sir?
Yeah.
It's dream
It's a
come
kind of
true.
testing script.
You can call it a script, or you assume it's a Python program. Okay.
Okay, sir. Okay.
You assume it's a Python program. Okay. What you should give the program? You should give your own program as input. You have written a Python program, say adding two numbers. Okay. To this miracle program, you will give this input of your adding two numbers program. And this miracle program, what it is going to tell you?
Whether it is going to halt or not halt.
Yes, it is going to halt or continue running forever. Okay. First of all, I want all of you to appreciate that this is a useful program. Yes.
It's a dream come true, more than useful.
Yeah.
Definitely.
It's a dream come true program. Okay. More than that, I will say it is more than that. If there is such a miracle program, then what one of the audience has suggested, it is going to be bigger than solving all Raymond's theorem or Fermat's theorem. Okay. It is going to be much bigger. Can you guess why it is going to be much bigger?
Because you can put 100 plates on a towers of an eye and still expect to get it solved.
You can, yes. You can write your program. For example, you can say, if Raymond's theorem is true, then run forever, else stop. That is the program you write. And then you ask the program, miracle program, is this going to terminate or not? All of you are catching the logic? What is the program you have written? See, what is the miracle program expecting? The miracle program will expect your program. And what is it going to give you? It is going to tell you whether your program will halt or not. Now, what have you asked the miracle program? What have you submitted to the miracle program? You have submitted a code which is written like, if the Raymond's theorem, if the Fermat's theorem is true, for example, then run forever, else stop. Okay. And now you have asked this miracle program, does this program end or not? Now miracle program has to tell you whether it ends or not. In other words, it is telling you whether the Riemann's conjecture or your Fermat's theorem is true or not. Okay. Is this clear? I want some response. I am expecting an answer.
Yes, sir.
Yeah? Clear.
Yes,
okay,
sir.
thank you. So if such a miracle program exists, then is it going to solve all our problems? Yes, it is going to solve all our programs, because any question you want to know, okay, any question you want to know, you can pose it as a halting problem. Okay. For example, you want to know whether, suppose you have a box, whether you can pack 26 balloons or 26 balls in that box. Okay, you know what size of balls are there. You want to know whether you can fit in certain number of boxes. Okay, certain number. How are you going to ask this miracle program? You are going to write a program that tells you, if it fits, then run forever, else stop, exit. Okay, and you ask, does this program run forever? Okay, then it is going to tell yes or no. If it tells yes or no, then you know whether you will be able to pack or not, right? Okay, so you can extend it to a ridiculous level. You can say, suppose you want to know whether you are going to get a job next year. Okay, how are you going to ask the miracle program for that? Anybody? Let me
Based on our
yeah.
Yes, sir.
Tell me.
Yes, sir. Based on our skills and experiences, whether we can get a job.
No. All that is not needed. It's a miracle program. Okay. So what you do is, you just ask, if I am getting a job next year, run this program forever, else stop. That you write and give it to your miracle program. The miracle program should tell whether it is stopping or not. No. So if it is stopping, then you know you're not going to get a job next year. If it is not stopping, it means that you are going to get a job next year, because you told, the program tells you, if you are going to get a job next year, it should run forever. Okay. So you have only put that in your program. Okay. So a miracle program, if it exists, would do miracles. Is it clear? Okay. Okay, fine. So all this, what does all this mean? What is the conclusion of all this? Anybody? What is the conclusion of all this? No such program exists. Okay. No such program exists. Is it clear? No such program means which program? A program that is going to tell you when you can halt. Okay, whether a program will halt or not can never be predicted by another program. So it is an unsolvable problem. All of you, is this part very clear to all of you? I'm expecting answer here.
Yes, sir, clear on our side.
Yeah, great. So, participants, this is a very powerful thing. I just want to, not very deep or anything. I just want you to just think over this concept. This tells you that there are some problems which are not solvable. That is what I wrote here, unsolvable problems. Okay, I gave you one example which is unsolvable, which is a halting problem. How did I prove that it is unsolvable? I did not prove it. I want you to look at the proof. It is not very difficult. I want you to understand it yourself. You can very easily understand it yourself. But what did I do all this time is, I told you, if such a miraculous program exists, then it will be really doing miracles. Okay. So you should have anticipated that. Since we don't see such miracles happening in our daily life, we should have anticipated that it is not possible to have a miracle program. This is only a word I'm using. There's some magical program or some other programs do not exist. Yeah. So that is why this problem is called as the halting problem, and I'm telling you it is an unsolvable problem. Okay. Why did I bring this up? Because I wanted to prove that there are some problems which cannot be solved. Okay. Which cannot be solved at all. Okay. Mathematically well framed problems also cannot be solved. Okay. But all, so cannot be solved means what? It cannot be solved by a Turing machine. Okay. Since it cannot be solved by a Turing machine, it cannot be solved by any machine. Is it clear?
Yes.
So that is what the last line tells you. All computers are essentially solve the same set of problems. Okay. It is not that during the unsolvable problems cannot be solved today, but tomorrow we may get a better PC. No, that will not happen. Okay. If Turing machine can do, anything can do. If Turing machine cannot do, no computer, how advanced it can solve it. Okay. Again, I told you this is all before quantum. This is all before quantum. Okay. After quantum, things change a little. So Church-Turing hypothesis does not apply to quantum computers. Okay. Does not quite apply. There is a to quantum computers. Okay. So that is why there is an interest in quantum computers. That is why we are celebrating, we are waiting for quantum computers, because something that has stayed true for 100 years. Turing hypothesis, I guess, was in say 1920s, I think. Okay, so this has been there since 1920s. We are now in 2025. So something that has been there for 100 years will be proved incorrect when quantum computers come. Okay, clear? Okay, fine.
Yes, sir. Clear.
Yeah. So now I have explained to you what is a Turing machine and what is a Church-Turing hypothesis. Now I am going to say what are the unique capabilities of quantum systems. Why quantum? Why? Because I told you quantum computers do not do not respect church Turing hypothesis. Okay, they do not respect. That is, they are bigger than that. Okay, then you should ask the question: what features of them makes them so powerful? Okay, what features, what capabilities make them so powerful? Okay, so for that, I have to explain to you some concepts. Okay, so here this is a very important concept. I want all of you to pay attention, and maybe if you are making notes, I suggest you make no note of all that is written here, and look back after the talking over also. You see here, if you have classically, okay, let us look at a classical case. In classical system, what you have is, you have, suppose a system can be in two states. Okay, what do you call a system that can exist in two states?
Either it is a 0 or 1, or on or off.
Yes, perfect. It is either 0 or 1, on or off, right? Electrical engineers will tell you in terms of voltages, what do you do? I guess it is say 0 volt and 5 volt. Okay, I don't know. Right, you understand this language. This is called as a bit. Bit is what? Bit is something that can exist in two states. The two states are, say, 0 or 1, or it could be left and right, or it could be on or off, or it could be low voltage, high voltage. Okay, like that, or it could be. So you can think of something that can exist in two well-defined states. Okay, here, there. Okay, in terms of boxes, for example, something that can exist in two boxes, right? So suppose you have two boxes and there is a ball. Okay, suppose it is here, the ball is here, indicates it is 0. If I put the ball in this box, it indicates it is 1, right? This is a good example. If it is in the left partition, it is 0. If it is in the right partition, it is 1. Correct?
Yes.
Yeah. So these are all how your classical bit is there. A bit can exist in a 0 state or a 1 state. Okay, where the 0 can be realized in different ways. Okay, like somebody said, it is on, this is off, this is on. Your 1 is your on, or this could be in the left partition, this could be in the right partition, or this could be low voltage, this could be high voltage, whatever. Something that can be existing in two unambiguous. Nobody, there should be no confusion. Okay, you should not put a ball in between. That will lead to confusion. That is not allowed. But anything that can exist in two well separated states, they should be well distinguishable states, is called as a bit. Okay, it is known as a bit, right? Now in quantum, what happens is, we represent the states like you do classically. We represent it as 0 and 1. Okay, don't get perturbed by the strange symbol here. These are known as kets. What are they known as? They are ket. Okay, don't get perturbed. This is just a symbol to represent the qubit. Now it is known as a qubit. What you had bit, you add a q to it. The bit was already there classically. You added a q. What is this? This is a quantum bit. Okay, you added a quantum to it. Okay, so they are represented, again your zeros and ones are represented by this symbol. You put something in between, either a 0 or a 1. Okay, then this becomes a qubit. Okay, but qubits are much more powerful. Why are they powerful? Because you can make them exist in a superposition. Okay, this is a very powerful notion known as the superposition. Again, it is a very simple concept for physics people. Again, I apologize for spending so much time on simple concept, but this is for the benefit of non-physicists. So please bear with me here. I'm going to go in detail. We still have a lot of time. I want to make concepts very clear. So you have a state 0, you have a state 1. Is even a quantum, even a classical can do. But what classical cannot do is you can exist in a superposition. That is, the state can be a combination of both. Okay, you keep hearing this Schrodinger cat, no? Schrodinger cat. You will say it is both alive and dead. Okay, you will alive and dead. You would have read this, all of you. It is there in some fancy T-shirts. Also, people put. I attended some conference and they distributed this fancy T-shirts also. Okay, so where it is written, Schrodinger cat will be written as the Schrodinger cat will be written as alive plus dead by root 2. Okay, this is going to tell you alive means the cat is alive, dead means the cat is dead. But quantum mechanically, the cat can be both alive and dead. Okay, it can exist in that superposition also. Okay, this is where the quantum thing comes. This is a unique quantum thing where something can be in a superposition. It can be in a combination. Like I told you, suppose you have, if it is in the left side, it is if the ball is on the left partition, I told you it stands for 0. If the ball is in the right partition, it stands for 1. Okay, but the same ball can be in both. It can be in a superposition. If you want to draw a picture, you have to write it as a superposition. This stands for 0 plus 1 by root 2. Okay, forget about root 2. This is a normalization. This is to make the vector of length 1. Okay, that is not very important. Don't bother much about this square root of 2. But you can see that there is only one particle. Don't assume I have put two particles. No, it is only one particle. One ball only is there. Okay, but it can now, if it is a quantum ball, it can exist in both the partitions at once. Is it clear? This is known as the superposition. Okay, superposition means something that can exist. Okay, another example, another practical, I mean real world example is, suppose you have two energy levels are there. Okay, if your particle is in this energy level, you call it as 0. If your particle is in this energy level, you call it as 1. Okay, if it is 0, if it is 1, then the state is 1. But the particle can be in both ground state and excited state. This is called as the ground state. This is called as the excited state. So the state of the system could be ground state plus excited state by root 2. Okay, this is known as this is the square root of 2. This is known as the superposition. Is it clear, all of you? Okay, anybody has any comments to make here? I will wait for an answer. Is it clear?
Yes, sir, it's clear, sir.
It is
Yes,
clear.
sir, it's well clear.
Yeah, thank you. So what I am telling you is that anything that you can imagine can exist in two states. It can also exist in a superposition. Okay, that can quantum systems exist in superposition? No. Okay, suppose I have a coin. Okay, I want more audience participation. Suppose I have a coin. Okay, what states can a coin exist in?
Head and tail.
Yes, head and tail. So if it is a classical coin, what are the states? You call, say, H and T. Good, right? Head and tail. Okay. How will you represent these states in quantum? You can write it as a ket head and ket tail. Okay. These two states are anyhow there classically. They are there quantum mechanically. But quantum mechanics has what speciality? Yeah, participants, I am expecting an answer.
It exists in both head and tail.
Yes, how do you write that state?
Superposition.
Yes, is it clear? It can exist in both heads and tails. Okay, if it is a quantum coin, okay, don't ask me where are quantum coins. They are there in the lab. If you visit my lab, or if you visit any lab, there might be some activity in Oasis Institute also. You will find that there is no quantum coin as such. They cannot show you a quantum coin, but there are other physical systems where this superposition is very much evident. Okay, that I will, as I go along, I am going to introduce you to them. So many of those physical systems can be shown to be existing in a superposition. Again, I want to bring to your notice that it is not just this kind of superposition, not just a plus. You will be also having, you can also have a minus. Okay, you can also have, why only equal superposition? You can also have unequal superposition. Like, for example, you can have, say, √3/2 heads plus 1/2 tails. Okay, what does this mean? Don't get perturbed. What is the square of this? What is the square of this quantity? What is the square of this
3/4.
quantity?
3/4, sir.
3/4. That is the probability of getting heads. Okay, if you make a measurement on this state, 3/4, whatever is there, that number, you take its mod square. Okay, this in general can be a complex number. You take its mod square. Okay, in this case it is mod 3/√3/2 square, that is 3/4, that is 0.75. That is 75% of the time this is in heads, and 25. What is 1/2 square?
1/4. 1/4.
1/4. What is 1/4?
25%.
25% of the time it is in tails. Is it clear? Okay.
Yes, sir.
Yeah, great. So what does it mean? The states can be in a superposition, and it can be in a, suppose you have yeah, what is the okay, suppose I have 1/√8 and 1 by, yeah, oh, excuse me, just let me make a small correction here. Suppose I have 1/√8 plus root heads. Okay. Now, what is the probability of getting heads here?
25%.
It is 1/8. 1/8 is the fractional probability of getting heads. And what is the probability of getting tails?
7/8.
7/8. Okay. So this is like, it is also a superposition, but it is mostly tails. Is that clear?
Yes,
Correct now? It is mostly tails.
Yes, sir.
But there is only one particle. Don't assume it is like you have put it in this state where if you make a measurement, you will see that there is a probability of 1/8 to get heads, and there is a probability of 7/8 to get tails. Is it clear? Okay. Suppose I write P times H. H is the head, plus square root of 1 minus P times tails. Okay. This is a general state, right? What is the probability of getting heads?
P.
P. What is the probability of getting heads? Tails?
1 minus P.
1 minus P.
1 minus P. So the total probability is 1 as you expected, right? Okay. Right? Total probability has to be 1. Okay. But very interesting concept is, like, for example, I can write a state 1 by root 2 head plus 1 by root 2 tails. What is the probability of getting heads?
50%.
50%, half. What is the probability of getting tails?
50%.
50%. Okay. But suppose instead of plus, I put a minus in between. What is the probability of getting heads? It is the same 50%. Probability of getting heads is 50%. But what is the probability of getting tails? I told you the mod only matters. What the modulus only matters. The sign doesn't matter. So it is still 50%. So it is 50% for this and 50% for this. Okay, clear? It is the same. The probabilities are same. Correct? Yeah. But the physics is different. These two states are very, very different states. Okay. Only in terms of these probabilities, they are same, but the states are very different and their physics and their behavior is very, very different. Okay. So that is what gives you more richer physics. Is that clear? Okay. These two probabilities are same, but the physics is different. Suppose I take another state, 1 by root 2 h. I am writing in the rightmost corner, plus I times 1 by root 2 tails. Okay. This state again, I told you for probabilities you have to take mod square. So I here doesn't matter with respect to probabilities, but with respect to other physics, it definitely matters. And then you are going to have totally different physics. Probabilities are same, but the states are not same. States are different states. They are not same states. Okay. So what is the meaning of this difference? Why this difference is important? You will know as we go along. Okay. But at this stage, you understand that these numbers, they are called as the relative phase. What you put in between, the sign or any complex number you put, they are the phases. Okay. They are the phases. PHASE, phase. Okay. These are very, very important in quantum mechanics. They are very important in quantum mechanics. Okay. They are not important with respect to the outcome probabilities. That much is correct, but they are important in other aspects, which I will tell you as we go ahead. Okay. Shall I go to the next slide?
Yes, sir.
Okay. Okay, great. So now this is the one I was telling you. Okay. Now see here, I told you that you are permitted to put complex numbers here, not just real numbers. Correct? These numbers are complex numbers. Let me write it down again. These numbers, suppose you have a state 0, you have another state 1. You can make a superposition C1 times 0 plus C2 times 1, where C1 and C2 are what? They are what?
Probabilities.
They are complex numbers. They are not necessarily real numbers. I told you, na, they can be negative, they can be positive, they can be real, they can have imaginary part also. Is it clear? How do you get the probabilities? Mod C1 square is going to tell you, okay, I will put C0 and I will put C1 to 1. Okay. So mod C0 is going to tell you the probability of getting 0. Mod C1 square is going to give you probability of getting a 1. Is it clear? Okay. Mod C0, mod C1. Okay. So the phase does not matter. You remember, na, complex number is R e power I5, or you can write a complex number as x plus iy. You remember these notations, no? So what is mod of x plus iy? Anybody?
So x square plus y
Root
square.
of x square plus y square.
Yeah,
X square plus y
it is
Square
square
of
root
x
of x
square
square plus y
square
square.
plus y
So
square.
mod square is just, we require anyhow mod square. So it is x square plus y square.
Y square.
That alone matters. So in this case, what is the modulus of this quantity? What is the modulus of this particular quantity? I am circling the polar coordinate. C is equal to, what is the modulus of this quantity?
R, sir.
R, thank you. So only R matters, the phi doesn't matter. This phi, what is it, this phi called as? In complex phase. It is called as the phase. The phase doesn't matter as far as the probabilities are concerned. Only the mod square matters. So your R0 and R1 only matter. The phi 0 and phi 1 do not matter. So that is only with respect to probabilities. Otherwise, these states are all different. Is it clear? Let me repeat the example I gave you. 0 plus 1 by root 2, 0 minus 1 by root 2, 0 plus I times 1 by root 2. All these are different states. They are all different states. Only the probabilities of getting 0 and 1 in all the three cases are same. The probabilities are same, because don't get confused. Some places I'm writing different, some places I'm writing same. Listen to me very carefully. The probabilities of getting 0 and 1 are same, but the states themselves are different. They are different states. Okay, they behave differently. Okay, what is the difference? I will come back to it later. Okay, so this is the one I was telling. Suppose you have, so now suppose you have 0 and 1, you can make a superposition. In terms of complex superposition, you can make, right? So you can make any state of a sphere, the surface of a sphere. Okay, this sphere is known as the Poincare sphere or Bloch sphere. Or I suggest you make notes of this. If you are interested, I request you to make notes and look for these keywords. Don't assume that I am teaching and you have to copy. Not in that sense I am saying. I am telling that you just write down the keywords so that tomorrow you look up in the internet, you will understand it much better. Okay, me explaining in online and all may not impact much, but you, when you look up for these keywords, you will understand. With this background, you will understand much better. Okay, that way this program will be very helpful for you. Okay, so you have this sphere. What is this sphere? This sphere is going to contain all possible superposition states. I told you, you can have a superposition 0 plus I times 1, or 0 minus 1, or 0 plus 1, or 0 minus I. Like that, you can have many more states. Every state on the surface of the sphere is a unique superposition state. Is it clear? Okay. Does it give you a feel for what states are possible on the quantum system? Yeah, it should give you a feel for how much you can. So this is a general state. Something, suppose you call something spinning up. Okay, you look at this particular picture. Wait. So you look at this particular picture. This indicates that it's a spin up. Okay, suppose it's an electron and it can exist in two spins. Okay, this is suppose spinning counterclockwise. Let us call it as up. Spinning clockwise, let us call it as down. Okay, then this is spin up, which can call it as 0. Spin down, you can call it as 1. But interestingly, if it is a quantum particle, it can exist in a superposition of both the spins. Okay, so it is like it is both spin up and down simultaneously. Okay, you clear? Fine. But when you make a measurement, I told you, you are going to see either it is spin up or it is spin down. Okay. What this combination is going to tell you, what is the probability? The probability of getting spin up is mod alpha square. Probability of getting spin down is mod beta square. Okay. Is it clear? Yes. Okay. Now there is a notion of entanglement, very powerful notion. Entanglement is like, it is also a superposition. Okay. But here, suppose what happens is that, suppose you have a state, I'm going to write a state of superposition. I'm going to call it as, suppose the state, suppose there are two particles. I can write their joint state as 0, 0 plus 1, 1 by root 2. What does it mean? It means that either both the spins are up or both the spins are down. Okay. This is the two particle system. That is why I'm writing, instead of 0 and 1, I'm writing 0, 0 and 1, 1. Okay. So this is a very special state. 0, 0, it means both the spins are up. 1, 1 means both the spins are down. 0, 0 plus 1, 1 by root 2 means it is in a superposition of both spins up and both spins down. Okay. But very strangely, what it tells you is that, suppose I make a measurement on, okay, suppose I have a state 0, 0 plus 1, 1 by root 2. Okay. Suppose I have a state like this. Okay. Then I make a measurement and I find one of them is up. Okay. Then I will also find other one is up. If I find one of them is down, I will also find the other one is down. Is it clear? Okay. Okay. I want an answer here. I want you to focus here. So what I was telling is that, suppose I have a state 0, 1 plus 1, 0 by root 2. What does it mean? It means that it is in a superposition. This plus indicates that it is in a superposition. What kind of superposition? When the first one is up, second one is down, or the first one is down, second one is up. Okay. This is in that kind of superposition. That means that if you make a measurement and you found first one is up, then automatically you will find second one will be down. Okay. These two are not physically connected, mind you. They could be very far away. Suppose they could be 100 kilometers separated. But still, if you make a measurement and you find it is up, and then other fellow makes a measurement, he will automatically find that it is down. Okay. So this is known as entanglement. It is, you look at this picture, the left bottom picture, it is like these two are magically connected. They could be very far away particles, but their state is entangled. Entangled means they are in a very strange mixed up state, strange combined state, where if one of them is up, the other will be down. It has to be down. Is it clear? Any questions? Anybody has any questions here? Okay, so let me proceed.
Hello,
Yeah, yes.
sir. Whether plus and minus sign indicates the direction?
No. Plus and minus sign do not indicate the direction. That is a good question. What she is asking is whether 0, 0 plus 1, 1 by root 2 or 0, 0 minus 1, 1 by root 2. What do they mean? Whether plus minus indicates a direction? No. The 0 and 1 indicate the direction. 0 means direction is anti-clockwise, 1 is clockwise. Okay, that are indicated by the states. This plus minus do not indicate directions at this stage. What it indicates, I will tell you later on. Okay, at this stage, they do not, they are just coefficients. Okay, clear?
Yes, sir.
Okay. Okay, let us go ahead. This part I will This is the, okay, this part I am going to explain to you a little detail. This is known as a glued tree. Again, I request you to write down this word, phrase glued tree, and look for it in the internet. Wikipedia, very good article is there. Okay. Here you assume, okay, all of you are able to see what is this picture. The tree, everybody must be familiar, na? This notion of a tree diagram. Yeah, we are all familiar with the tree. Na? You have a root node and you have two successive nodes. Each one has two successive. So in data structures, I remember we have learned about trees in data structures, right? Yeah. So here, yeah. So let me proceed. So you have a tree here, and here you have now two trees. You have now two trees here. This is one tree, this is another tree. Okay, all of you are able to follow what I am saying? You have two trees. What do you call the last part of the tree? Anybody remembers what is the name?
Leaves.
Leaf, yeah, leaves. Leaves. Yeah, they are the leaves because they don't have any further thing. So they are the leaves. Okay. So what are the leaves of this particular tree? These are the leaves of this particular tree. Similarly, you take the leaves of another tree and you join those two. Okay. So you have joined them in a very haphazardical manner. Randomly you have drawn. Is it clear, all of you? Okay. Okay. I am going to explain to you. It may not be very evident what is it that we are doing here. Okay. But now you assume there is a fellow who is walking randomly. He is starting. It is like you brought a blind man. Okay. A blind man. He is going to move to the left or right. Is it clear? Okay. There is a blind person. He is brought at this particular node, at this entrance. There is a, all of you are able to read the word entrance here.
So in that case, the tree will become a graph again, sir?
What?
Because if we connect the leaves of a two tree, then it's no more a tree, it becomes a graph again.
It is a graph. Yes, it is a graph only. It is no longer a tree. Okay. Yeah, that is right. So what you do is you connect in this entrance. You have each fellow. Now you assume there is a blind man. Okay. He has been brought here. Why blind? Not necessarily blind. He doesn't know the way. Okay. He has come to entrance. He wants to reach the exit. Right? Now, can anybody suggest how he should go from entrance to exit?
We can have avalanche walk, KVL walk.
No, it is like this is a maze. You assume that he can only move one step to the left or right. Okay. He doesn't know how these are connected. That is why I told you you can only tell him, suppose, okay, let us start the game. Okay. Suppose he is there here. Suppose he is there here. What do you suggest? How he should go next?
Heuristic.
Heuristic, yes. So let us say he goes here. Then what? He takes a left. This is the left, no? He's standing here facing this side. So he goes to the left. Then what he should do? Either take a left or a right. Let us say he takes a left. Then he takes a right. Now again he takes a right. Up to here, up to this plane he can come, right? No matter what he does, up to here he can reach, right? All of you are following what I'm saying?
Yes, sir.
Yeah. Why there is a I can sense, although I'm not seeing any of you, I can sense there is a discomfort. So let me repeat what I'm saying. There is a person here who is standing. He has to reach from the entrance. He has to reach the exit. So he has to choose between left or right. You cannot tell him anything. You just have to tell him. You means you or him. He has to decide whether he should move left or right. Okay. Suppose he moves to the right. Then he comes here. Then he moves to the right, he comes here. Then he moves to the left, he goes here. Moves to the left, he goes here. So no matter what he does in one, 2, 3, 4. In 4 steps, he will reach here, correct? This line he will reach, some point in this line. Okay. But what happens after he reaches here? He can take this, okay, and then he can take this, then he can take this, then he can take this. So now it is not clear how he should go. Is that fine?
Unless he keeps a level count.
Yes, the level count is not available to him. Yes.
Then we can feel sorry for him.
Yeah, we can only feel sorry for him. Yes. But is it very clear that what is the probability? Suppose he is not even doing deterministically. He lost all hope. I told you he's a blind man. Okay. He is a blind man. Okay. He can only feel the wall and move, for example. Okay. So he cannot even make count. I don't know, having eyes also will help, but we have made it even more miserable. He is a blind man. Okay. He can only feel the wall and go to the left or right to the right. Right. So randomly he will decide. Correct. So what is the probability of him exiting?
Very low.
Very, very low. Okay. Let us assume exit is special. It should not happen that poor fellow is blind. He comes here and then he goes here. That does not happen. Let us assume once exit is there, there is some good smell or good air conditioning is there in exit, so that he will know that he has reached exit. Okay. So once he reaches here, then that fellow has won the race. Okay. So all of you agree that this is a very difficult problem, correct? Okay. So I have made a simulation here. You just see this particular simulation here. You understand that this is okay. So without much ado, okay, you can read this, but reading we will do later. All of you focus your attention on this region. On the region. See here, what happens is there is a finite chance that he comes back also. Okay. Once he comes back, he goes backward only. He cannot go back into the game. Once he comes back to the entrance region, you understand what I'm saying? Once he comes back to the entrance, he cannot go back again. He will go outside. Okay. So this region is his reflection region. This region is the intermediate region, and this is the transmitted region. Okay. So here he goes out. Once he goes out, he will go out of the system. Is it clear? So because I want to have some success, failure, and process regions. Is it clear? So this is a reflected region. Is what region? Is it a success or failure?
Okay, failure.
It's a failure. It's a failure. What is the success region?
Transmitted region.
Transmitted region is a success region. This region is the in process. He is still trying. He is neither succeeded nor he has lost. It is a stuck region. You are stuck. You can succeed or you can fail. Correct? So now you look at, I have done 2 walks here. Quantum walk is there and a classical walk is there. Okay. Quantum walk, I told you, can walk in superposition. He can do both. If he has to do left or right, he can do both of them simultaneously. You can assume that is a feature. Okay. Because I told you a quantum walker can be taking 2 paths simultaneously. So that is going to give him an advantage. Yes. So what happens is, now just observe this particular animation after 29, 38, 40 steps. Now look at what happened after 49 steps. The blue region is quantum walk, the blue diagram. So you will see that almost 90% of the time by 49 steps, more than 95%. Okay, you understand? Let me mark this region. This is the region I'm talking about. This is about 92% of the time. There is a probability of transmission. Transmission is success in quantum walk. The blue region corresponds to quantum. The orange region corresponds to classical. Okay. So whereas what is the classical winning probability? Just about 5%, less than that. All of you are following? Okay,
Following, sir. Following, sir.
You're following? Great. So don't get perturbed by what is being done, how it is done. I will explain to you in some other context. But just to see what is done, and you try to appreciate what is the message. Okay, all of you, again I'm going to play this animation. Here you see already let us halt here. Just keep the topmost, there is a step count is there. So now this is a step one, nothing is there. This is a beginning. Let us assume this is a beginning. The one step is over. Okay, it starts from 0, so one step is over. You see here by 15-16 steps you have 80% probability of exiting, of succeeding. This is the success region, right? So quantum walks, you will successfully exit the path by more than 95%. But classically, what happened in the classical path? There is only 5% probability of succeeding. There is a more than 95% probability of getting stuck. All of you are understanding this one? Okay. Again, let me run this. You see here the probability of success in quantum walks. The blue region corresponds to quantum walks. Orange bar corresponds to classical walk. You see that it is increasing more and more. Is it clear, all of you? Okay. This is a picture of the same thing here. You can, that same picture I have drawn there, I have put in terms of the plot here. As you see, with the number of steps, the classical probability is going very, very slowly. You can see the orange plot here. After 50 steps, the probability is only less than 0.05, whereas here it is close to 95. Is it clear? 95% probability. So quantum walks can escape much faster than classical walks. All of you pay attention to this left bottom points here. Quantum walks can escape much faster than classical walks. Okay. Likewise, you have, this is a paper, Universal Computation by Quantum Walk. This kind of work is introduced by Childs. This is the name of the physicist, name of the computer scientist, Childs, Andrew M. Childs. That is what is written here. Childs glued tree. This is known as this tree. You understand, glued tree, because you have joined the trees together like this. Okay. So you can see that it is going to be this kind of a plot. Is this clear? Shall we go to the next slide, all of you?
Yes, sir.
Yeah, great. Thank you. So, there is another phenomenal paper. This is by Wouters and Zurek. Again, I am telling you the names also, because again I request you to write down these names and look up if you are not already familiar. These are the remarkable people. Wouters, in the earlier paper I introduced the name Childs. This is the second one, is by Wouters and Zurek. Okay, these are the remarkable people. They introduced what is known as the no cloning theorem. No cloning theorem tells you that you cannot copy a quantum state. You cannot copy an unknown quantum state. You cannot make an exact copy. Suppose you have a state. How is the state written? I told you it is written as some C0 times 0 plus C1 times 1 by root 2. All of you remember this? What I had by root 2 nahi aayega. We will have only this kind of superposition, right? This state you cannot make a exact state. You cannot copy an exact state. So you cannot replicate an unknown quantum state. Okay. This is known as the no cloning theorem. Quantum state cannot be cloned. Okay. So this is a very powerful statement and it has very much restriction. So this is going to have lot of impact when you are learning about quantum computation and also in quantum communication. All of you understand why it is important in quantum communication? Anybody can guess why no cloning theorem is important in quantum communication? Any wild guess?
Because the communication should be the valid one. It should not be like a hypothetical, like it can be either this or either that one. It should be a precise one.
No, not in that sense. I'm asking why you can. I told you what is the meaning of cloning. Cloning is to make a copy of. You cannot copy a state. Okay. I'm asking you why that is an important notion in quantum communication, in any communication. Because you don't want your data to be copied, no? You don't want any, suppose you are sending some information, nobody should make a copy of that information, right? Okay, so this is going to help you. Quantum no cloning theorem is going to have very beneficial effect in quantum communication. Is it clear? Okay. Okay, so let me go forward very quickly. I have now run out of time. So let me very quickly go through. So there is this Feynman, again, all of you must be familiar, is the Nobel laureate, American. He is of a USA person. He is a Nobel laureate. I think this paper he has written in 1982. Okay, most of his he's one of the original people worked in quantum. So his main works have come in 1930s, 40s. Okay, so by the time this paper is in 1982. So this is a very old paper. Okay, very when he was at a very old age, he has written this paper, 1982. Whereas his best work was come in 1940s. I don't quite remember when he got his Nobel Prize. That must also be in 1950s. Okay, so this he must have written this during a very late age. So you have this simulating. This is the paper, simulating physics with computers. Okay, so where he has suggested how you can use quantum mechanics to get very good simulations with computers. By then already classical computers were available. He has written how to do, classical was there, but how to simulate physics problems using quantum computers. Okay, so there is another, I told you about Turing machine. There is a notion of quantum Turing machine where you make the head as quantum. Okay, so this idea was given by, again, Benioff and Feynman. Okay, so and this is the David Deutsch. This is his paper. This again you should see the date here, 1985. Okay, David Deutsch, again he is a UK mathematician and physicist. He has given the theory of quantum theory of Church-Turing principle. I hope you all recall what I explained to you about Turing machines and this. They have added quantum features to this one, and they have studied what can be done. Okay, this is Umesh Wazirani. He is again one of the very acclaimed Indian origin people. Very original contributions in this field. Okay, he is of Indian origin. Again, he is based in US, but originally from India. So, so this is a paper where the first recorded usage of the word qubit was written. Okay, so in this paper, this is in 1995. Again, 10 years have passed already. So in this paper by Schumacher, this is the Benjamin Schumacher in the US. He has written that the term qubit was coined in just means in fun, when they were having just casually somebody said quantum bit, so qubit. So this paper was the first one to have used the word qubit. Okay, so here you can see in the abstract he has used the word quantum bits or qubits. Okay, so this is where, because the title of my talk said I have to give some history, so I thought I should tell you some historically what. This is what can be expected from a quantum computer. Okay, it should have a scalable physical system with well characterized qubits. Okay, that means what should be, how should your physical system be looking like? Okay, you should have you should have something that can exist in a superposition. I told you, na, you should be able to generate a state in a superposition like this. Okay, so your hardware system should be able to support that. So that is known as the de Vincenzo's criteria. He has told you how to construct quantum computers, what should be the features of a quantum computer. Okay, so that is given by this particular criteria called, that is how to physically implement the quantum computer. So this has come in the year 2000. Okay, the physical implementation of quantum computer. So you should be able to have qubits, you should be able to initialize them, that is you should be able to set them to a definite state. Suppose, that is you should be able to put them in a particular well-known state. Then you should be able to have, this part I will explain later, you should be able to be doing some universal operations. All of you remember universal gates in computation, in logic, Boolean algebra?
NAND and NOR gates.
NAND and NOR gates. Like that, you should be able to have a support for universal quantum gates. That is, you should be able to do some quantum operations which are universal. Okay, clear? And there's, you should be able to measure the state of the system. Okay, so he has given 7 criteria. This he is a theoretician. In 2000, he has given, if somebody wants to build a quantum computer hardware. Anybody has anything to say? Okay, so let us proceed here. So quantum hardware, there are different methods here. There are superconducting quantum. I am now discussing how quantum computers are hardware, how they are realized. Okay, so there are different ones. I will not get into much here. There will be, I am hoping there will be talks covering this subject. So you have trapped ion computing, neutral ion atom. This is the most popular one, superconducting quantum, superconducting devices. This is what most of the current day super quantum computers are built on this technology. These are different technologies, mind you. There are, and this is only not all, this does not cover everything. Not everything is covered. Okay, clear? You understand, all of you? See, you have classical computers are only of one type. Classical computers, the brand may be different, but the hardware is the same, right? But here in quantum computers, there are about 10 to 15 very popular hardware platforms. Okay, that again tells you that the system is still not commercially ready, because there are people are trying different methods of doing quantum hardware. Is it clear? Okay, is this point clear to all of you? Okay, so let me proceed. And these are the major players here. I have again this picture I carried from this particular article by this particular person. You have in photonics. These are the companies working in NV centers in diamond, nitrogen vacancy centers. In cold atom, these are the companies working. With respect to error correction, these are the companies. And with respect to electronics for quantum computers, these are the different people. With respect to cryogenics, cryogenics is low temperature, because particularly in superconducting quantum computing, you need pretty low temperatures to work. Okay, because you require the effect of Josephson effect and superconductivity to manifest. So that can happen only at low temperatures. So you require cryogenics also. So these are the major cryogenics people. So these are the different companies. Again, I suggest you to look up these names. These are the major players in different platforms. Okay, and this, yeah. Okay, I have skipped this particular quantum circuit slide. Maybe in my next talk, I will do this one. And this is the paper where the first notion of quantum computers was discussed in 1995. The title says Simple Quantum Computer. Okay, so this is although the machine which we envision has little practical use, at the first statement itself, he is saying it is of little practical use. Okay, so there he has solved what is known as the Deutsch problem. So this is the very first notion of quantum computer. This has come in 1995. Isaac L. Chuang, this person, he has a book on quantum computing. This is you can call it as the Bible of quantum computing books, a very standard reference textbook. Again, I suggest you to Nielsen and Chuang. This is the book, Nielsen and Chuang. Everybody should have, anybody interested in quantum computers should have that book. Okay, fine. Okay, so I will skip the Grover's algorithm. Again, I guess there are talks on this one, so I will not talk about the Grover's algorithm. I will skip this part also. Quantum supremacy also I will discuss in the next talk. I will go to the machine learning part, and I am going to wind up my talk here. So there is this notion of why machine learning. Okay, again, I'm telling you, I'm not an expert here, but I have some ideas which I'm sure the other speakers are going to help me in taking this better, communicating this to you. Okay, in machine learning, you have a notion of state space. This is like the set of all possible configurations or states that a system can exist in. Okay, suppose you have a coin. Suppose you have 100 coins. Okay, each coin can exist in how many states? Classically, forget quantum. How many states each coin can exist in?
2 states.
2 states. 100 coins can exist in how many states?
2 raised to 100.
2 raised to 100. Okay, this is quite large, isn't it?
Yeah.
Yeah, anything that goes 2 to the power of n, this growth is like exponential growth. Okay, so your state space grows exponentially. Okay, once your state space is growing exponentially, any calculations that you want to do, so if your state space grows exponentially, then it becomes more and more difficult to work in that space. Okay, suppose you have some problem which has 2 power n configurations. 2 power n configurations. So 2 power n. So if you have n configurations, then if you have n degrees of freedom, then you have 2 power n configurations. Suppose you want to search for something in 2 power n configurations, it is going to be very, very difficult for large n. Is it clear? Suppose 2, because you have heads and tails. Suppose you have k such choices and d variables, like 2 states d coins, then it is 2 power n. If you have k states and d coins, then it will be k power d. So this is going to be a very large dimensional system. So this is known as the curse of dimensionality. Okay, like for example, one quick problem I will tell you. This is a traveling salesman problem. Again, all of you have heard of this problem. Most of you would have heard of this problem. Okay, so here you have, suppose this is one simple example I have taken. Suppose there is a salesman. There is a salesman. He has to visit 4 cities, A, B, C, D. All of you are able to see the cities A, B, C, and D. Okay, what are these numbers? Can you guess what are?
Cost.
Yeah?
Cost or distance?
Distance between the cities.
Or it could be distance. Yeah, it could be cost, or it could be the distance, or it could be the time it takes, or it could be the toll. Okay, whatever. Suppose his company is providing the car for him, then what he will cost does not matter. But then still, what he will have to optimize? Time. He wants to visit all the places in a minimum time. So this could be one of those parameters. All of you are clear with this? Now the question is, he has to visit all the 4 cities. He has to visit all the 4 cities in the minimum possible cost function. This could be cost function. Okay. Suppose this is a distance, then he wants to spend minimum distance. Okay. Or he wants to spend minimum time. Okay. So how should he start? Whether he should do ABCD, or whether he should do BCAD, or whether he should do CABC. Okay. And he has to come back also, CABC, CABDC. Okay. He has to go somewhere and come back. Or he can go here, here and come back. Also, all of you are understanding that this is not a brute force search you cannot do, right? This has exponential paths are available, correct? So you have the curse of dimensionality, you have exponential search you have to do. You have to search over exponential places. Okay, this is one problem. Another problem is knapsack problem. Okay, what is a knapsack problem? Knapsack problem is somebody told you that they want to gift you certain items. 15 kgs of something somebody wants to gift. You have carried a bag that can take 15 kgs, right? You have a bag, you have carried a bag to your shop, it can take 15 kgs. Somebody has told you that you can take up to 15 kgs, any of the items, any number. Okay, so how are you going to maximize your benefit? Because the price is also given. This is $1, this is $2, this is $10, this is $2, this is $4. Okay, so what items will you carry? How many of them to maximize your earning? You understand the question? This is known as the knapsack problem. Okay, what is the worst item to carry? Anybody answer me so that I know you are all listening?
And the low value items are the worst. Low value and high weight.
Which will be?
Rock. Don't carry the rocks. Look for diamonds and gold.
Yes, that is right. Don't carry the rocks. Look for the diamond. Okay. So this appears to be the no. Don't buy this. Right. Don't carry this because it is carrying 12 kgs, but it is giving you only $4 of value. Okay. It is not very valuable. Perhaps this appears to be better. Correct. I don't know. So we have to like that. This is only 4 objects are there, but it has only 4 objects, but it has. But suppose you have hundreds of objects like that. Okay, is it clear? Does this sound like a very theoretical problem, or do you imagine that it is a real problem? This is an example of a real problem. No, let me repeat the question. Does this problem, solving this problem, will you think will be helpful in real life or not?
Yes, sir. Real life problem only.
It is real life problem only. Okay. The way it is written, it does not look very real life, but you can imagine real life problems which can convert into this problem, correct?
Yes, of course, sir.
Yes, of course. Like maybe Amazon people, when they are sending deliveries, maybe they try to do this way only. I don't know. Okay. So this is a real life problem. Okay. So this involves a brute force search. Suppose you want to do a brute force search, then it is very, very difficult. Okay. So then where does quantum come in the picture? Okay. Quantum comes in the picture because quantum computer can explore state space exponentially faster. Again, I have put this picture. This picture was shown to you earlier. This was shown earlier, correct? Okay, this picture you are familiar. Why did I bring this picture again? This picture told you that quantum computers can work in parallel and they can search something very efficiently. Okay, so for this kind of problems, quantum computer can search your solutions parallelly. So they can, even if they are exponential also, they can be made to work efficiently. Is that clear? Now, how it does may not be clear at this stage, but is it clear that quantum computers may help? Are you able to appreciate that?
Excuse me, Dr. Kadiri.
Yes.
Shall we extend the time?
No, I will just wind up in another 5 minutes. Yeah, you
Okay.
have a. Let me wind up in 5 minutes. I am done.
Okay, thank you, sir. Thank you.
Yeah. So, so I have just made that this is the one example of quantum artificial intelligence, where you have convergence of quantum computing and artificial intelligence. This goes by the name quantum machine learning is more popular name. Okay, so this is going to lead you to a paradigm shift with, because classical AI systems suffer with the problem of dimensionality. Okay, so quantum computers, I told you, they have the inherent parallelism is going to help in solving this particular problem. Okay, so this has valuable applications involving high dimensional data, drug discovery, material science. I have seen your schedule also. Very interesting topics are there, where people have specifically, there are lectures on how quantum and AI is going to help in these subjects. So I am also keen, looking forward to listening to those talks. So there you will understand how quantum computers are going to help in these sectors in better machine learning. Okay, so this I will skip here. This is the picture that generally people talk of. You have to find a global minima, which is somewhere here. But if you don't do your optimization properly, your solutions are going to be stuck in a local minima. So you need a good, your global minima is here. Sorry, not here. Your global minima is here. So your system will be stuck at false minima. Okay, it will be a local minima, but it cannot be going to a global minima. Quantum methods can help in that direction also. Yes, I will skip here and I will stop it here. Thank you very much.
Really an excellent session, Dr. Gururaj. Thank you very much for your time. And if there is any queries, please ask. We shall take 2 minutes for that.
If you have any queries at some other point of time also, I will be glad to take your questions over WhatsApp or over email also. I will be glad to respond to the audience.
Okay, if there is no queries, so even you can contact Dr. Kadiri through mail to familiarize with quantum computing. Always you are welcome to present your queries here also. So we can also help you to connect with Dr. Kadiri. So you can get along with him in your interest in learning the quantum computing. Thank you, Dr. Kadiri. Thank you very much for your time.
Yeah, thank you. Thank you.
Now we'll be moving on to the session of Dr. Sabarathinam. Professor Shivakumar will be giving a nice introduction about Dr. Sabarathinam.
Thank you, everyone. I wish we had more time for Dr. Kadiri. Unfortunately, we have to move on. It's my honor to introduce our second eminent speaker of the day, Dr. Sabarathinam Srinivasan, who is a professor in the School of Data Analytics and Artificial Intelligence in Faculty of Computer Science, Higher School of Economics, HSE University in Moscow, Russia. Dr. Srinivasan has vast and rich experience in research areas in data analytics, artificial intelligence, and machine learning. Doctor has published widely in reputed international journals and has been involved in several collaborative projects across the countries. His academic work has focused on developing innovative frameworks for data-driven decision-making, particularly using AI and advanced computational methods. Today, he will be delivering a valuable session on the topic, the potential impact of quantum computers in data analytics. With his deep expertise and international exposure, we look forward to his perspectives on how quantum systems can transform the way data analytics is carried out in the near future. Thank you and welcome, sir.
Good evening, sir. Am I audible?
Yes, sir. You are audible.
Okay, let me share the screen. Is my PPT visible?
Yes, sir, it's visible, sir.
Okay. So, good evening, one and all present here. Before going to explain my today presentation, I would like to thank the chairman of Oasis Institute of Technology and Dr. A. Anto Kingsley, principal of the college, and Dr. J. Palanivel sir and co-coordinator Joshua sir for organizing this wonderful FDP event. And I would like to thank inviting me to take part in this wonderful program. So, good evening to one and all here. Today, I am going to explain the topic such as the potential impact of quantum computers in data analytics. Before going into the detail, let me introduce my college, my university a little bit. So, we are in the topmost world university ranking. We secured 197th rank internationally, and industry income wise we secured 85th rank, and among the Russian universities we are securing the second rank, which we are doing in variety of research areas. And explaining about my faculty of computer science, currently we are having 23 bachelor and master programs in various domains of artificial intelligence and data analytics. We have 19 internationally recognized laboratories, and we have 512 faculty members, and as of course more than 5,000 plus students. And we have bachelor programs, master programs, as well as doctoral programs. So to get in the admission, we need to pass the like interview and direct entrance test. So there are many steps. You can follow the university anytime. And I am working in the data analytics and artificial intelligence department since 2024. Previously, I am working in the laboratory of complex system modeling and control. So I am currently taking the course Modern Concept of Dynamical Neural Networks for the master students of artificial intelligence and data analytics students. Okay, so this is my today presentation content. First of all, I would like to introduce why we need the quantum computing and why it is matters in recent times. And I can jump the basic of quantum computing. I think the previous speaker is beautifully explained about the basic concept of quantum computing. So maybe I can skip few slides, and I can compare the classical versus quantum data analytics, what we are achieving so far, and what is the current scenario in the quantum computing era. And I can show you some crazy programs about quantum algorithm which we are going to use recently developed IBM libraries. After that, I will explain about real world applications and some case studies. Further, I would like to explain about what are the challenges we are facing currently and what are the limitations of the quantum computer in present time. Yes, sir.
ఇంకా మనకి కన్వీనర్ కోటాలో 887 మందికి ఇంకా 101 మంది రావాల్సి ఉంది సార్ ఇవాళ ఈవినింగ్ స్టేటస్. సర్టిఫికెట్స్ వైజ్ మనకి 780 మంది రిపోర్ట్ చేశారండి. 887.
Please switch off your microphone. Let the speaker proceed.
ఇందులో మనకి ఒక్క నిమిషం సార్. సర్టిఫికెట్స్ 415 మంది సబ్మిట్ చేశారండి సర్టిఫికెట్.
Sir, I think
let there not be any
ఫాలో అప్ చేస్తున్నాం సార్. కేటగిరీ బి లో మనకి 154 మన తరపున అయినాయి సార్. 80 వాళ్ళకి ఇచ్చాము కదా సార్ మనం.
Sir, I think you can mute the speaker.
ఇంకా 99 మిగిలినాయి సార్. ఈ 99లో కూడా మనకి
Please don't disturb the speaker. Whatever be your queries, you can post it later, please.
Shall I continue, sir?
Yeah, please. Please, Sabarathinam. You can.
Thank you. So we already are running out of time, so I can quickly try to solve this slide. Okay. So after that, I will show what are the implications we can do as a teacher, as a stakeholder, as a academician. I will give some interesting links to start with the quantum computing research area. Finally, I will conclude the talk. Why quantum computers matters? So let's start with a simple but powerful question. Why should we, as a educator, as a researcher, care about quantum computing right now? The answer lies in the data explosion we are experiencing. Every day, we generate over 300 exabytes of data globally. The data coming from social medias, sensors, scientific instruments, and healthcare system, etc., etc. So that's like filling millions of car drives every single day. And what do we do with this data? And we are going to analyze it. We build AI models, we extract insight, some information from the data. But here the problem coming. The classical computers are hitting their limits. Moore's law are slowing down. We can't keep shrinking transistor forever. We should move other researching scenario. Tasks like training large AI models or simulating complex systems now requires massive data centers and weeks of computation. At the same time, the demand of computational power, especially in AI and machine learning, is growing exponentially. Think about deep learning models with billions of hyperparameters or optimization problems in many scenarios such as logistics, finance, genomics, etc. These are not just a big, they are computationally intractable for classical system at scale. So this is where quantum computing comes in, not just a faster computer, but as a paradigm shift. It does just do more calculation per second. It computes in a fundamentally different way. By harnessing quantum mechanics, it can explore vast solution spaces in parallel, offering potential exponential speed up for specific critical problems in data analytics. So why does this matter to us as a faculty? So first of all, research. So we are going to start with the research. So quantum computing opens new frontiers in optimization, machine learning, cryptography, and simulation, etc. It is a gold mine for interdisciplinary collaboration right now. So we can collaborate physics, computer science, mathematics, engineering, and even biology and economics people. Second thing, the curriculum development. Our students are entering a world where quantum literacy will be as important as coding in future. We have the responsibility and opportunity to shape the next generation of quantum ready professionals. And the last, interdisciplinary. So means funding and innovation we can talking about. National missions like India as well as US, they are open a very good massive programs such as Quantum Initiative and pouring resources in this field. Now is the time to get involved, to build a labs, propose a project, and collaborate across the department. So quantum computing is still emerging, but the window to lead, to innovate, and to educate is open right now. So let me quickly jump into the quantum physics and understand about the quantum computer as fast as we can. So in the classical computer, as we know, all the motions and the Kepler law, the planetary motions, celestial motion, everything we can know about through the classical physics. But when we go with the quantum level, we could not explain about many things. So as a atom level. So why this is important? Because of some futuristic applications. So the quantum can explaining about the microscopic phenomena which classical physics does not explain it. So quantum theory successfully explained the behavior of particles in the scales of atomic level, and also including discrete energy level of electrons in atom, photoelectric effect, and the stability, etc., etc. And it is also giving the fundamental understanding of nature, which the classical physics does not. So it introduces interesting concepts such as wave particle duality, superposition, entanglement, uncertainty, etc., which challenge classical intuition and have profound philosophical implications. So for understanding this quantum scenario, we should understand the three important concepts such as wave particle duality. I'm not going to explain in detail because everyone knows about this wave particle duality through the double slit experiment. What double slit experiment gave us? So the electron, if you are sending the electron from here, so as we know, let me take a pen. Okay. So if you are sending the electron in the beam, so it is also behave like a particle, like it is going like a pack, and it is also penetrate as like a wave. So we have a fundamental question rises like, is it a particle or wave? Then we come to the conclusion like it is a wave particle. So from the wave particle duality, the double slit experiment confirms the electron's nature. And the second one is a superposition, as the previous speaker explained in beautiful manner, like what is a superposition. But let me explain little detail. So in the classical time, people think that the atoms look like electrons are traveling through the nuclei, and nuclei have neutron and proton in the static manner. But in the later time, we discovered electrons is like a cloud on the nuclei, and in the electron cloud, the electron can be anywhere, anytime. So once we measure the position of the electron, it can be anywhere. It is called the superposition, and also it have a 360-degree possibility, and it have up spin, down spin, any kind of spin once at the superposition before we measure. Okay, so you can simply consider the small example like a fan. It's rotating very fast. So without measuring anything, we can say the wing at anywhere in the 360 circle. But once we measure, we could understand where is the blades of the fan. So this is called the superposition. Before we measure, we could say the particle can exist anywhere. And even though we can explain through the Schrodinger cat as the same uncertainty explanation, may or may not case. So before we open this Schrodinger box, we can say the cat is alive or dead. It means it's a superposition state. The third example is the quantum entanglement. So as we know, the electron entanglement means it's a phenomenon where two or more particles become linked together in a way that their quantum state are correlated, even when separated by a large distances, like in the distance between one galaxy to other galaxy. Measuring the property of one entangled particle instantaneously influenced the corresponding property of the other, regardless of the distance between them. This is called the spooky action, which is called by the Einstein. It's a fundamental aspect of quantum mechanics and key resource for the quantum technologies. So as we know, the zero state mean upspin and one state mean downspin, we can say. So before we measure, it's look like the same. Once we measure, we can tell the state of the two entangled particle. It must be one is a downspin and the corresponding one must be the upspin. So this is a basic idea we need to take as a message from the quantum entanglement to understand the quantum computer. Okay, so so far we can understand about what is the superposition and wave particle duality and entanglement. So let's talk about the qubit. A qubit or a quantum bit is the basic unit of quantum information, similar to how a classical bit is the basic unit of information like traditional computing. However, classical bit, as a previous speaker explained about zero state, one state, and also explained about the superposition state, and the qubit can exist in the combination of 0 and 1, which means it is exist in the superposition state. So I'm not going to explain in detail. We can consider here like the classical bit, it's look like 0 and 1. So we can make the combination between 0 and 1 by making the gates operation, Boolean algebra, and make the arithmetic and logical operations, etc. But for the qubit superposition, we have a large sphere. So in the sphere, the entangled particle may be anywhere. And when we are measuring the particle, we can explain the state of the state, means the qubit, like whether it is up spin or down spin or whatever. Okay, so the classical computer works is, I mean, almost we all are very much aware of this thing. This computer technology, what we are trying to do, we are making the device smaller and smaller day by day. And we are reaching almost the point where the classical physics is no longer suitable model for the law of physics. So as we know, in 1960s or before the time, we are generating a transistor or vacuum tube. It's look like a 2-room or 3-room size. But in and recent times, we are creating the transistor, ICs, and processor. It's a combination of millions transistor inside. So we can quickly go through this Moore's law. What Moore's law is means giving the detail to us. So from 1900 to 2025, you can see the graph. So you can see Moore's explain 2 power n, which means the evolution of the transistor in n times each decades. So it is also happening the same as Moore's tell us. So in the 1940, we have a solid state relay, and we have created the vacuum tube, and we have the transistor. So the transistor made calculation per second, like you can imagine the size. And from the transistor, we are creating the integrated circuit as started from IBM PC, Pentium series, 1, 3, 4, etc. After that, the I series is coming. Now we have reached i7, i9 processor. So as some point of time, you can see there is no evolution here. Why? Because of the quantum tunneling effect. So the small schematic diagram, I try to explain what is the quantum tunneling here. So before this is a transistor. So what transistor is doing? Once the base current is activated, then the current flow started from this C to E. This we all know this is a single transistor operation, and if the base current is off, then the current is stopped. It's like a switch based on the base current. So consider this beam is like a base, and this is a huge size. So what happened when we are trying to make a device smaller and smaller, which means the transistor size is reducing faster and faster, such as previously transistor exists in a big size. After that, we created an integrated circuit which consists of n number of transistor inside the ICs. After that, you can imagine the core i7, i9. There are billions transistor inside the processor. So our ultimate aim is to integrate more ICs for very fast operations. So what happened if you are decreasing the size of the transistor or ICs? We need to reduce the size of this transistor as well. So the base beam are also size reduced. So it is like very thin in recent times. So in our base size is less than 5 nanometer, which is very much greater than blood cell. So you can imagine the base size. So due to the base size, the electron is free to move without any dependency on the base. So this is called a quantum tunneling. That is what we could not able to produce more and more thin size material. May or may not, means up to now we don't have that much thing. So due to the quantum tunneling, we could not depends the transistor theory forever. So we need the alternative computational power. For that, this quantum is emerged. So we can compare the classical and quantum computer. This classical computer, what it is doing step-by-step calculation. For example, if you have a password 011, let's say we have a 3-bit operation. 3-bit operation means we have a 9 combinations. So what classical computer do? It will check one by one, and which one is fit for the expected one, then it is giving the output. So it is we can call it as the operational speed, and the speed of the operation depends on the clock speed of the computer and what processor that we are using in our PC, and how many calculation per second it can do. So it depends on the speed, like in the classical computer. But we are talking about the quantum computer. As we know, it exists in the superposition state. So there is a probability like 0 and 1 state, mean up spin and down spin state. So what we are doing with the means quantum computer, we are giving the superposition input and we get the superposition output instantly. So there are operators which emerge in recent times, like Groover operator can remove the unwanted attempt. So we can directly get the result in one go without any step functions. So from these basic ideas of quantum computers and qubits, are we going to replace the classical versions of the computer, or do we use the quantum computer for some specific task, and how we are going to resolve those issues? The quantum circuit, as we say, is a model for quantum computation, similar how the classical computer uses logic gates to manipulate bits. So the key component of the quantum circuits are qubits, quantum gates, and measurements. Qubit, as we know, the basic unit of the quantum information represented as lines in the circuit, and the quantum gates. So in recent times, we have few gates such as Hadamard gate, Pauli X gate, CNOT gate. Those gates are doing the small operation, like to trap the superposition states. And we need to measure based on the gates, like at the end of the circuit, qubits are measured, collapsing their superposition into classical state. Okay, so why quantum circuits are more important to constructing the quantum computers? So the quantum circuits are the foundation of quantum algorithms like Shor's algorithm, Groover algorithm, etc. So means so far we have few algorithms. In future we have many algorithms. That what our aim is to do. So they allow us to harness the power of qubits to solve problems that are infeasible for classical computers. In short, we can say the quantum circuit is a sequence of quantum gates applied to qubits to perform computation, leveraging quantum mechanics to solve in a new way. Okay, so this is the Hadamard gate function. We have 4 gates, qubit state, and the 4 qubit input, it's going to give the H gate operation, and all the qubits connected each other, and it's a very famous quantum circuit, Hadamard gate. So you can see there is a measurement applies in each qubits level. So each level of computation, each step. So we need to measurement and collapse operation we need to do that I am going to explain in the later slides. So due to the measurement collapse, we can understand what is the state of the qubit at the particular time. Okay, so let's talk about how the quantum computer works. So we need to understand the three important principles. First one is the quantum gates and circuits. As I explained in the previous slides, we have this Kadamat gate like this. We need to give the classical bit value 0 and 1 through the Kadamat gate. This gate function take the input as a qubit, and it can go to the quantum gates such as C0 or other gates, which I explained in the previous slides. We have only 3-4 gates, and again we need to put the input in the Hadamard gate, and the Hadamard gate will give the classical bit operation 0 and 1 with the collapse and measurement operation. So this at the end we are giving the classical input and we are getting the classical output in the quantum circuit scenarios. So such as you can imagine the 4 qubit shows in the G file. So this is the step size of our operation, like from 0 to 15 step. So each step we can see the state of all the qubits, like up spin or down spin. So we have a 4 possibilities, which means we can send 4 bits of information in a different sector. Like each time step we can measure the state of the qubits. And the second interesting information is the measurement and collapse. So during the quantum computing operation, we need to do the measurement and collapse. So before measurement, as we know, all the qubits are in the superposition. So it means it can exist in the 0 state, up spin or down spin. And during the measurement, the act of observing, when you measure the qubit, this superposition ends instantly. The qubit collapse into one of the classical state, either 0 or 1, and you get the classical bit output 0 or 1. As we see, like we are giving the operation. So in any collapse, any measurement, we get 0 and 1, means classical output. And this is called collapse. After measurement, this is called collapse state. Collapse means we are stopping the operation. If you measured 0, the qubit is now definitely in the state of 0 state. And if you are measured like 1, it is in the 1 state. So any future measurement without further quantum operation, which means without further step, we will get the same result because it is no longer in the superposition. So this small code I can explain in the end of the talk. So I am creating a small Python code to explain the measurement and collapse. So why this important in data analytics? So quantum algorithm, like we have a Groover operator and HSL operator for solving the linear systems. So we use superposition and entanglement to process many possibility at once, but you can't read all the information directly because when you measure, the state collapse to just one outcome. So the art of quantum algorithm design is to use interference to amplify the correct answer before the measurement, so that when collapse happens, you are very lucky to get the right result. And there are also some common misconception about measurement and collapse, like the statement like measurement just read the state. No, it is changing the state, and you can measure the qubit multiple times and get different info. No, after the measurement, the collapse is happen, the collapse stay the qubit in the same state. And the third misconception is quantum computers give all answer at once, but the answer is no. You only get one result per measurement. You need repetition charts. So these charts we are going to perform as a Python code. I am giving the 1000 charts, so we can see how we can measure the state of the qubits. Okay. So the third important concept for the quantum computers, noisy intermediate scale quantum era. So there are three terms: noisy, intermediate scale, and quantum. We know qubit superposition and entanglement, and let's talk about where the technology actually stands today. Because while quantum computing sounds futuristic, we already building and using a real quantum machines, but they come with big limitation, and that brings us. You will hear a lot of words like NISQ pronounced. The NISQ stands like the same, noisy intermediate scale quantum. It is not a library brand or model. It is just a category that describes the current generation of quantum computers we have access to, both in labs via the cloud. Let's break down each and every terms. Noisy means in the classical computers, which can run billions of operations with near perfect accuracy, quantum computers are incredibly sensitive. As we know, a tiny vibration, a stray electromagnetic wave, even a small heat, all of this can disturb the quantum state of the qubit. When that happens, we get errors in the computation. This is called decoherence, and it is very important issues in recent times. So the qubit forgets its quantum information in milliseconds. So these devices are noisy, meaning they are error prone. And second one is the intermediate scale. Today quantum processor have somewhere between 50 to some few hundred qubits. Means as research article come out from the literature from IBM, Google, they tell us like we are generated 50 qubits, 300 qubits, 1000 qubits, etc. But that might sound impressive, and it is compared to just a decade ago, but it is not nearly enough to run the powerful quantum algorithm we often read about, like Shor algorithm for breaking encryption. These machines are intermediate, not small, not yet large. And third is the quantum thing. That is obvious. These are devices that use quantum machines to process information in ways classical computers simply can't do. So what we are taking means what we take home message in the perspective of data analytics. The NISQ era devices are real but limited. They run quantum circuits but only short ones. They can demonstrate quantum effect but not with fully reliability. What does this mean for data analytics? We can't yet use NISQ devices to analyze big data set directly. You can't feed a millions of rows of customer data into 7 qubit machine. But what we can do, use them in a hybrid model, where a classical computer plus the quantum processor, we can solve a specific problem. It is like we can say it's a hybrid models. So the meaning is we are not going to replacing the classical model. We are experimenting with quantum enhancement, and that actually existing for academia. Because NISQ devices are accessible, you can log into IBM Quantum Experience right now and run a circuit on a real quantum computer for free. So that means I'm giving the link of this particular quantum experience. So once I complete the talk, I can share this PPT. So you can log in this quantum IBM machine and you can run a small qubit circuit for free. That means faculty and student can learn, test algorithms, and contribute for more accuracy. Okay, so in summary, what we are take home from the NISQ era, the full of challenges, but rich with opportunities for education, experimentation, and innovation. As a educator, this is the perfect time to start exploring quantum computing, not as a replacement for what we teach, but as a new frontier to expand our student horizons. So here I am giving some current players of experiencing the quantum circuits. So I can ask you, you can personally go through those websites. You can check the quantum circuit. You can play with this. You can understand what the quantum circuit actually do. Especially IBM, up to 133 qubits we can access. So it is available via cloud. Focus on improving the gate fidelity. And also Google, Rigetti, IonQ, D-Wave company, they are creating many number of qubits for specific operations. Okay. Let's quickly go through the classical data analytics. So what we are doing in the classical AI scenarios. So we are doing the task, like what are the tasks? We are doing the clustering, classification, regression, optimization, etc. Like to do the forecasting and predictions. And what are the tools we are using? We are using Python, R, Spark, Kaggle, Google Colab, etc. Whatever the available IDE, we can use it. And bottlenecks are scalability, high dimensionality, and very hard problems. So the basic outlier of this classical data analytics, we have a data set. We need to pre-process the data, and we transformed the data set into the models, and we do the machine learning models like through the neural network, etc. And we need to do the evaluation with different metrics analysis like RMSE, F1 score, etc. So for understand confusion matrix, etc. So these are the basic asset of as of now we have the classical data analytics. So let me quickly explain what is this. So these are the encoder and decoder concept by using the attention mechanism. The upper side is showing the decoding time step. Like I'm giving only 6 time step, translating from one language to other language. What it is doing, the encoder send these three word as a matrix, and encoder sent to the transformer. Transformer have many birth and GPT, etc. So this encoder to send the encoded output, and it will also parallelly we are doing the same translated outputs, and it is decoding with this thing, and we are getting the translation. So we are using this classical data analytics. For example, transformer, we have an encoder decoder thing, and we have one side one language matrix means corpus, and another side the translated version corpus. So both corpus is feed into the encoder decoder, and each time step we can get the output. Like this is the way ChatGPT and other mechanisms are doing the operations. Like we need a large hyperparameter which are doing very fast. This what we need, but we could not have. That is why we need a quick operations strategies or algorithm. So if we have a quantum computer, we have a lot of advantages, especially in the data analytics. So the three important things: speed. If we implement the quantum computer in the perspective of data analytics, we can speed up like exponentially the task, and we can reduce the complexity where we handling the high dimensional data, and we can reduce the optimization problem like quantum annealing. So quantum annealing is a specialized approach to solving complex optimization problems. Unlike universal quantum computer, machine like D-Wave use a quantum effect like tunneling and superposition to find the lowest energy state. This is ultimate aim. Lowest energy state, as we can say in our classical data analytics, like finding the lowest loss function. And the example we have so far quantum PCA, principal analysis, component analysis, and we have quantum support vector machine and HH algorithm for linear system. So those data analytics tool like libraries, it's look like a hybrid model, which a combination means fusion of classical plus quantum ideas. So where the quantum computing can help in data analytics. The first one is a speed, exponential acceleration we can get. For the specific task, such as quantum algorithm offer exponential or polynomial speedups over classical counterparts. In recent times, we are doing all the data analytics and artificial intelligence for the unstructured data with a large dimension. So we have a n-dimensional, means hyperparameters too much, so it's very complex. But if you are implementing quantum computing, like such as using Grover algorithm or any new fascinating algorithm which can identify the pattern from the unstructured data, it will be a huge outcome. We can expect the exponential acceleration in the field of AI. And the second one is the complexity, which means high dimensional data. We are dealing with a high dimensional data as I discussed in the earlier slide. We are generating n-dimensional data in every day. So for analyzing those data, if you are implementing the quantum system, naturally represent and manipulate high dimensional vectors using superposition, it can encode 2 power n features with just the n qubits, like quantum feature space. And the third one, like finding the global minima, it's like optimization problem. So in recent times, a D-Wave company, like they are giving the quantum annealing, and also QAOA algorithm helps to solve hard problems like clustering, routing, and portfolio optimization. And it explore energy landscape using quantum tunneling, avoiding local minimas. Okay, so I can explain the recent algorithm which we developed, which I give the example. This quantum PCA, principal component analysis, uses the quantum phase estimation is to find the dominant components, exponentially faster in loading and processing classical data in quantum state, ideal for dimensionality reduction in high dimensional data set. So the dimensionality reduction is the very important concept which we are dealing with a high dimensional data set. So it is very useful for this principal component analysis, very useful for do these operations. And the quantum support vector machine, as we know, the support vector machine in classical data analytics like machine learning and other things. But now we have a quantum support vector machine library. It leverages a quantum kernel method to classify data in a high dimensional Hilbert space. It can find the patterns interactable for classical SVMs. So it is already testable on NISQ devices using variational circuits. And the last one, Hutch algorithm, which is Harrow-Hasidim-Liard algorithm, which is introduced in 2009. So it is actually solve the linear systems, and it is foundation for quantum regression analysis, differential equations, and small operations. Currently, it is in the theoretical for large systems. It's require fault-tolerant quantum computing. Okay, so from those understanding of classical computer and quantum computing ideas and hybrid models, what we achieve so far, we have real world relevance and we have a limitation. The promise is we have exponentially speed of in theoretical, like we have HHL algorithm, Grover operator, etc. But as far now, we have a practical limit. We can't able to do a large scale. We can do the smaller scale and linear system, etc. And it is naturally fit for machine learning task involving linear algebra and optimization. And it is the hybrid model runs on real NISQ hardware. And active research in quantum finance, genomics, artificial intelligence, etc. in variety of field. But we have a limitation such as the data encoding is bottleneck, means quantum RAM is not yet succeeded, and the noise limits circuits depth and accuracy, because when we see the quantum computer in real time, so it is keep in the very safest area, and it is avoided a small amount of noise, and it's very careful about the external temperature, pressure. So it is very limited. So it's also very costly. And the quantum advantage not yet proven for real world analytics task, and we have a shortage of quantum literate data scientists. Okay, so let me explain about this quantum machine learning. So quantum machine learning explores how the quantum computers can enhance machine learning tasks, faster training, better pattern recognition, and handling complex data. The core idea, we are going to use the quantum properties such as superposition, entanglement to process the data in way classical computer cannot do. We are using the hybrid approaches. Most practically, classical computer handles data for optimization, etc. And the quantum processor runs quantum circuit for computation. So here you can understand, like in the blue color, we are doing the classical way. We have the data. We are going to pre-process the data, and the pre-processed data put it into the measurement, which means a neural network or machine learning models, and we need to optimize. We need to reduce the error function, and we can update the model. This is for the one step. So each time step we are doing like CA approaches. But now the quantum machine learning, they are introducing the quantum circuit in middle. After the pre-processing, the classical input is fed into the quantum circuit, and the quantum circuit which we are getting as a quantum output means classical output for the measurement operation, and we are doing the same as a classical. So we can call it as a hybrid because we are fusing the two models, like in the classical thing and the quantum thing. So for achieving the quantum machine learning, we should know about the quantum neural network, because any machine learning algorithm running backbone of neural networks. So the QNN parameterized quantum circuit that act like an activation function. You can consider this is only for the activation function. So it is trainable via classical optimization, like as we are doing the gradient descent method. It can classify data and detect the pattern in high dimensional spaces. So why this is matters for the quantum neural network? It is potential exponential advantage in feature spaces via quantum kernel method, etc. Early evidence of quantum advantage in synthetic data tasks. So as for now, we have three libraries like QISKit, which is given by IBM. It is a full stack quantum software development kit, and Pennyland library from Xanadu, built for quantum machine learning and automatic differentiation. And last one for TensorFlow Quantum. It is coming from the Google, and it integrates with TensorFlow for hybrid models. Okay. So we can see the hands-on simple quantum classifier using the Pennyland library. So the variational quantum classifier using the quantum neural network. The circuit learns two classes using quantum rotations. The classical optimizer tunes the quantum parameters. So this code also I am going to explain in details. Okay, and the real world use case we can see for the industrial applications. The quantum computing is not just theoretical. Industries are already testing it. In finance, the firm like JB Morgan are using quantum algorithm to optimize investment portfolios, balancing risk and return across thousands of assets, a task that grows exponentially complex. In healthcare, stimulating molecules for drug delivery is classically intractable. Quantum computer naturally models quantum system, making them ideal for simulating chemical reactions. In logistic, companies face massive optimization challenges. Think of delivering package across multiple countries with minimal fuel. So quantum annealing with finding the minimal loss function means lowest energy state. It can give the promising speedups. And the climate modeling requires simulating quantum interactions in molecules like carbon dioxide, etc. A perfect fit for quantum hardware. And in the academic research perspective, as a academia and a researcher are exploring quantum machine learning for clustering and classification tasks, outperforming classical models on specific data set. Let's take portfolio optimization. It is a case study. Suppose you have a 4 stocks. Classically evaluating all combination is manageable, but with 50 asset, you can imagine it is become infeasible. So it is making too much complexity. Quantum computer encodes each asset as a qubit. Means we can say if it is selected 0, it means not chosen. If it is 1, if it is chosen. The QA-OA algorithm evolves the quantum state to minimize the risk and maximize the return. So this is the important concept, like minimize the risk and maximize the return. This is a portfolio operation. It is some crazy code I'm going to give you. Like we can find the minimized risk and maximize return of this portfolio. While still it is in the early stage, JB Morgan has shown that even on today's noisy devices, quantum inspired models, means hybrid model, can outperform classical heuristics on small data set. This is a great example of the hybrid quantum classical workflow where quantum computers handle the hard optimization part. So this we can, I am going to explain with the code. The code start pull all the qubits as a superposition, means all possible portfolios at once. And we apply the cost unitary, encodes our Hamiltonian, and mixer unitary, and repeat the layers to find the better outcome. And we measure in the particular instant, like collapse measure, as I explained previous slides, and pick the first one. So let us quickly go all the 3 codes. Hope all you see the see my collab IDE. So for doing the small simple quantum circuit, we need the QSkit library to make the circuit possible. So we here I'm going to use the only 1 qubit of circuit, means only 1 classical bit for measurement. I am using the hard mod gate. Putting into the superposition, means it is a chance for 0 and 1, and I'm going to run a 1000 runs. As a result, we have a counts of 0 and 1. What we are expecting 50% of 0 and 50% of 1, like, but what is actually happened, let's start. So if we run in this particular run, we have 528 1 and 472 zeros, which means the superposition state in the particular instant. So if we count again, the state is changing. It look like generating a random number, but we are doing with the quantum computing, means qubits. So we are using the quantum circuit with only one quantum circuit with 2 superposition state. So we are measuring the particular superposition state in a 1000 times in instantly. So in every instant we can have the different qubit outputs. It's a playing. You can increase the qubit circuit number, and you can see the outputs. These are the basic understanding of how the quantum circuit can run. The second library is the Penny Lane, which is coming from the Hodo one some company. So this library also I installed. So this Penny Lane to build and train a quantum machine learning model. Consider the 2 qubit quantum device we are creating. The quantum circuit encodes input angles RY, RZ, and qubit 0 and C0 gate, and we are using the trainable weights before measuring output on the qubit. The same like what I explained in the slides. So we are introducing the qubit, means quantum circuit inside the classical data analytics, and we are trying to find the outcome of the quantum machine learning algorithm. The same like you can understand from the code. So it is giving the cost function within the four instance steps. So we are getting the weights like weight which is computed from the qubit circuit. So if we are changing again, we are doing the calculation again, we will get the very small changes in the weights. So which means if you are using as a optimizer, it can give the quick optimization result in means compared to the classical versions. And the third one as the crazy portfolio instance. So we are going to see the returns and risk analysis. So I am giving the some initialization of these 4 stacks, and so the code is little long. You can go through one by one, and we can understand because it is the code is given by JB Morgan. So expected return, the best fit for this state, we have a 5 state, and we have a covariance sigma, and we have a portfolios chosen by first one and the last stacks. We have a risk, very less risk, and our asset is 2. We have a high return in this particular run. If you are running again, we will get another good run. So what I am trying to say from this qubit libraries and operation, we are in the beginning state, but still we need to improve the library as well as this quantum computing understanding more and more. So let's continue with the talk. What are the challenges and the limitations we have in various perspective like hardware, software, etc. While the potential is exciting, we must also realistic. Quantum computing is still in the early stage, and several major challenges remains we need to tackle. First, hardware limitation. Current quantum computers are noisy and error prone, and qubits are fragile. Small disturbances cause decoherence, meaning they lose their quantum state quickly, and we have very less quantum states like 50 to 100 or 300 qubits. We need far fewer than needed for large scale, large data set, fault tolerant computation. Second, on the software side, tools are still immature. As we see in our code, we use only the library and we see the state. So we need more and more updation. There is no standardized programming framework yet. Platforms like Qiskit, PennyLane, like Circ are evolving. But debugging quantum code is very complex because when we launch the measurement and collapse, we can predict only one state. We can't go the backside, and we can't go front side, means next step. We can, so that is why it is very complex, and integration with the classical system is also a challenging one. Third, there is a critical talent gap. We need more people who understand both the quantum physics and computer science and quantum related researchers, developer, educator, etc. This is where academia can play a vital role. And finally, let's address the common misconception, quantum supremacy. Like Google in 2019 claimed that it create a quantum computer solved some specific task faster than the classical computer can do, but that task was artificial. It does not mean quantum computers are practically useful yet for real world data analytics. So while progress is very rapid, quantum computers won't replace classical ones anytime soon. They were likely to work alongside them in hybrid models for foreseeable future. So as a faculty development programs, like as a faculties, for the academia, we need the take-home message for the implication. So first one is the curriculum development. Quantum computing is no longer just for the physicist, like physics concept. It's time to integrate foundational concept into computer science, mathematics, and statistics programs. And research opportunities like quantum computers opens door for interdisciplinary research, combining computer science, physics, engineering, and all other domain areas like healthcare, finance. The faculty can explore quantum machine learning, optimization for smart cities, or even quantum enhanced simulation in various fields. This is a chance to lead cutting edge collaborative project. And for the funding, it's very important. So governments are investing heavily. For example, India National Quantum Mission, they are aim to boost the research and development with more than 6,000 crores. Similar program exist globally, like US and other countries are investing more and more money for more funding opportunities in particular quantum field to support infrastructure, fellowship and innovation ideas and create opportunities for the faculty to propose new research initiatives. And we talking about the collaboration is very must. Partnering with industry like IBM, Google or other startup companies. There are many, as the previous speaker shown, variety of companies. So they can provide access to quantum hardware and real world problems, hosting quantum hackathons, workshops, seminars. So this can engage students and build a vibrant academic community around emerging technology. So as a teacher, as an educator, we are not just preparing students for the job. We are shaping the future for technology by embracing quantum now. Let's getting started. The good news is you don't need a quantum lab to start exploring. Several free hands-on tools are available today. You can access real quantum computers and simulators through IBM Quantum Experience. It's cloud-based and completely free for educator and students. And Google Circ is another open framework, great for designing quantum circuits. If you are looking for to learn, like top universities such as MIT, TU Left or Stanford offers online courses on etc. For coding, like you want to know about the library like QSkit, PennyLearn, both are open sources. So as I show in the example, so it is well documented and perfect for experimenting with quantum machine learning. So finally, joining communities like QWorld, QSkit, Slack channels, they most hosting the workshop, seminars, etc., and have active forums where educator and researchers can collaborate. So before conclude these things, we can see some recent advancement in the real quantum computers. The quantum computers they are trying to make in the with the following criteria, like it is a vacuum. They are going to create in the vacuum places, creating as a vacuum environment. It is avoiding the quantum vibrations. It's caption about the temperature and photon emission free nature. So the first quantum supremacy, Google explained they are creating 54 qubits in 2009 something, and they just generating the random numbers using pi, and they claim like it create the random numbers which the classical computer can create for 10,000 years. It create 200 seconds. And IBM claims it is not at 10,000 years and it is only 2.5 years generating the random numbers with the recent supercomputers. So, but still we can see it is wow. And also they announced the Willow, like it's a quantum hardware. And the next important thing in the Nature article, after this declaration from the Google, IBM declare we are creating around 100 qubits, with again the same supremacy, and they published in the Nature journal in 2021. And after that, Microsoft say they are creating Majorana 1 processor. I think you are heard in recent times, like it is launched very recently. So it is a world first quantum chip powered by a new topological core architecture and capable of solving meaningful industrial scale problem in a years, not a decades. So they are about to produce the processor. And also they are published one article in Nature, like by creating the 100 cube 10,000 qubits. These are the important papers for the roadmap of quantum computers. Okay, so how they are those quantum computers? So for achieving qubits, they are making they are taking the help from the material science people. They are creating some new material using this technology, like ion traps, superconducting circuits, neutral atoms, photons, radiation vacancies, topological quantum computings, etc. So there are many players which they are tackling any one of the concept above and try to create the supercomputing chip. And also in the same time, we have a problem by explaining this qubit as well as quantum computer. So people also come into the same Nature journal, like Microsoft claims quantum computing breakthrough, but some physicists are skeptical. So it's a doubt of the output. And talking about the market, the market grew very drastically after 2019 or 2020 onwards. Now people are investing too much stacks in the supercomputers. So in the future outlook, by concluding all this, we can say what does the future hold? In next 5 to 10 years, we won't see the quantum computer replacing the classical one for sure. Instead, we will see hybrid systems where quantum processor handles specific complex tasks within classical data analytics workflows. Think of quantum as a specialized accelerator like GPU for certain machine learning or optimization problem. Looking further ahead, the ultimate goal is fault-tolerant quantum computers, machines with millions of stable qubits capable of running complex algorithms reliably. That's likely decades away, but progress is very much accelerating. And this is where we as a educator play a crucial role. We are not just teaching the current generation, we are shaping the minds who will build and use these technologies. So introducing quantum concept early, encouraging interdisciplinary thinking, and fostering curiosity will be the key to preparing students for a quantum enhanced future. So you can see in recent news I saw in my phone. So there are many news coming out day by day about the quantum computer and quantum chips and qubit, etc. So you can understand the emerging speed of the quantum computers. Okay, so let's quickly recap what we are explored today. So first, quantum computing is not just about being faster, it's about using the principle of quantum mechanics like superposition and entanglement to process information in fundamentally new ways. So this gives it the potential to handle massive scale and complexity beyond classical limits. We have seen how quantum computers could revolutionize data analytics, especially for optimization, machine learning, and high-dimensional data analytics with the algorithms such as HHL and QS quantum support vector machine and QAOA paving a way. But it is all not ready yet. We still face the big challenges: hardware limitation, noise, and shortage of skilled professionals. Still, progress is accelerating both globally and initiatives like India's National Quantum Mission. So finally, and most importantly for us as educator and a researcher, academicians, stakeholder, so we have a crucial role to need to play. We can lead the curriculum development, interdisciplinary research, and preparing the next generation of quantum ready talent. So the future of data analytics may very well be quantum, and we are in the position to shape it. So these are the reference I referred and some important books. So this book already explained the previous speaker. So it's very important books, and this quantum experience you can go through and you will see how to construct small qubits and with a piece of quantum circuit. And you can also visit the quantum machine learning toolkit to learn what is the Q-skit, and you can use your data analytics or machine learning perspectives, or you can enhance or you can contribute to this library. So with all this, thank you very much.
Thank you, Dr. Sabarathinam. If there are any queries, you can ask the participants. Really, it was nice to listen to you, making a mention about the quantum support vector machines, quantum neural networks, that counterpart of all the classical things what is existing now, and it is how it is going to play a vital role in data analytics. Really, it was interesting. Thank you, Dr. Sabarathinam.
Thank you, sir.
Those who want to have any questions, you can ask or you can contact Dr. Sabarathinam.
I have one question regarding the quantum algorithms. So nowadays there is a many analytical problems involving a heavy linear algebra, and how close are the current quantum algorithm like some HHL or quantum PCA to be being in a practical on today's hardware?
So actually, this is a question we are still need to find the answer. Like all the libraries or the algorithms are in the very beginning state. We are solving only the linear regressions, very basic models. So we are creating such as very small number of qubits, but we need a large number of qubits to tackle huge amount of large data set, high dimensional things and optimization. So still the progress is going on. So that is why they are giving the open source for all the libraries to, like anyone can see the library and they can contribute their ideas.
Thanks.
So I can share the PPT as well as this Python code for you can just go through the links and you can understand some basic things like how to construct a small qubits, and you can understand also the quantum machine learning and using the quantum neural network and using the libraries. So it is very useful for you to start with a new era.
And thank you, Dr. Sabarathinam, for your valuable sessions. And tomorrow we are going to have a session on quantum computers and machine learning by Mr. Guncha Malik from IBM Quantum Ambassador, IBM India. And another session on algorithms for quantum computing by Dr. V.P. Ramesh, Professor, School of Mathematics and Computer Science from Tiruvallur, Tamil Nadu, India, Central University. And thank you. I will see you all tomorrow, 6 p.m. starting. Thank you.
Thank you, sir.
Thank you, sir.